Good morning, good afternoon, good evening, ladies and gentlemen. Uh, my name is Pranav Sharma. Thank you so much for joining us. It's such great pleasure of having a lot of you here today. Uh, so today's session, which is the last session in the Astroinformatics for Sustainable Development Policy webinar series, begins now. It will go until later in the evening. And we would be covering a lot of interesting ideas. We have talks and panels. The panels would cover regional global collaboration, space data requirements, and then eventually astroinformatics. Directly, we have Bernard, we have Juna, and we have Dan for their wonderful talks, which we would see in due course of time. I'm delighted and happy to welcome uh, uh, Professor Bernard Faneroff he's a South African astronomer. Fantastic work that he's done. He is a great radio astronomer, needs no introduction. He's been in the field for a great time. He's responsible for the Faneroff-Riley classification of radio galaxies. Today's talk that Bernard is going to uh, deliver is about global and regional collaborations in radio astronomy in the MeerKAT and SK experience. And all these talks that we are going and panels that we are having today are also being developed into white papers, which will lead to a common white paper and a policy document eventually for recommendations. Without further ado, may I now invite Bernard Faneroff.
Thank you very much, Pranav. Thank you very much to the organizers for inviting me. I'm not actually a professor. I only managed to be a doctor. So I'm going to talk about global and regional collaboration in radio astronomy based on our experiences in building the MeerKAT telescope in South Africa and our participation in the Square Kilometre Array global project. And the slogan that I've put there is build it and they will come. If you're prepared to make an investment in a very good instrument, you'll find that people from around the world will want to use it and they will work with you. And that is our experience with the MeerKAT telescope. So, no, not quite sure why these are not advanced. There we are. Okay. So as I'm sure you all know, the Square Kilometre Array has been a global mega science project from the beginning. The astronomers started thinking about it in the early 1990s. And as other speakers have said earlier, it's now the norm for mega science projects to be multinational because no single country can fund and implement them. But global projects by their nature are complex because they combine national objectives and also many different scientific objectives. And our experience has been that although you would expect scientists to be strictly scientific and rational, it doesn't really work that way. So the development and implementation of these mega projects is never strictly scientific and rational. There's always an element of negotiation and politics which creeps in. So it's important to agree as early as possible on the science, the design, the engineering, and the commercial objectives, and also importantly on the procedures. Even when you do that, they're never unambiguous. There's always room for argument. So the Square Kilometre Array started off with a steering committee of scientists in 2006. That was replaced by a committee which included government funding agencies. And so it was composed of scientists and bureaucrats. And then there was a board of directors of the SKA organization, which was a company founded in the UK. And now, of course, there's a treaty organization with a council, which is chaired by Catherine Chizarski. And the treaty organization now includes South Africa, Australia, the UK, China, France, Switzerland, Netherlands, Italy, and Portugal. Spain, Germany, and Canada are in the process of joining, I believe. And Sweden and India, I think, are working with their governments towards participation. But there's been quite a lot of progress, and infrastructure contracts have been issued in South Africa, and I believe they're about to be issued in Western Australia. So South Africa came quite late to this project. We only established the South African Square Kilometre Array project in January 2003, and we very quickly selected 5 possible sites, and we then carried out testing and characterization of the sites. And we sent an expression of interest to the International SKA Steering Committee in May of 2003. There were then all sorts of measurements and so on taking place. And in 2006, South Africa and Australia were shortlisted as the possible host sites for the SKA. Then a formal request for proposals was issued in 2010 by the International SKA Committee. And the site selection took place in 2012 based on a recommendation by an independent international committee chaired by Jim Moran from Harvard. And that committee recommended the African bid. The SKA Organization Board of Directors took a final decision in 2012 that the SKA mid-frequency and aperture arrays would be built in Africa and the low-frequency arrays would be built in Western Australia in order to utilize all the investments which South Africa and Australia had already made. So that's a picture of the way our site looked in 2003. You can see it's very arid, lots of low-topped hills, which provide a bit of protection against radio frequency interference. Top right, you'll see Professor Justin Jonas telling me where we should build our observatory and our telescope, and you can see how arid the area is. So in 2004, our South African Steering Committee decided to fund, design, and build an SK precursor telescope, which we originally called the Karoo Array Telescope, the CAT. And then our National Treasury gave us more money, so we called it Meerkat, which in Afrikaans, the local language, is more of CAT. We established a very good observatory site in the Karoo, which is the central part of South Africa, very arid. We acquired 14,000 hectares of farmland at that time. More recently, the National Research Foundation and the South African Radio Astronomy Observatory have acquired 130,000 hectares, as well as 79 servitudes to accommodate the whole phase 1 of the Square Kilometre Array. And that whole area is now being run as a wilderness park by South African National Parks. We had to connect power to our observatory site from the national grid. We had to upgrade the substation in the nearest town, a little town called Carnarvon. And we specially designed a power line which would minimize radio frequency interference. We had to connect to the national optical fiber backbone. We did on-site buildings, 2.5 megawatts of uninterruptible power supply. We reticulated the site, and we had to build 80 kilometers of road to the site. We were also able to persuade our parliament to pass a law called the Astronomy Geographic Advantage Act, which gives the Minister for Science and Technology in the government the power to regulate the whole of the Northern Cape Province, which is 45% of South Africa's land area, in order to ensure radio quietness. The original SKA design required a 3,000 kilometer baseline, which doesn't fit into South Africa, and our bid included 8 other African countries: Namibia, Botswana, Zambia, Mozambique, Mauritius, Madagascar, Kenya, and Ghana. So we started negotiations with their governments in 2003 to gain their support. The negotiations were led by our National Department of Science and Technology, and of course we worked with them. We were eventually able to get a resolution passed by the heads of state of the African Union supporting our bid for the square kilometre array. And we got very enthusiastic involvement over the years from universities and governments in our partner countries, especially because they were keen to build skills and expertise on the continent. So there are regular meetings between the officials, and the ministers meet at least once a year, usually in Pretoria. So for now, South Africa represents them all at the SKO Council because to be a member, you've got to pay, and it was felt that South Africa should do that. So here's a picture of what our proposed distribution of sites would be. On the far right there, you can see Mauritius, a dot in the ocean, then Madagascar, and then sites from South Africa all the way up to Ghana. Now, bottom left, you'll see one of our meetings some years back in Accra in Ghana of the officials. And on the right, you'll see one of the meetings of ministers, which, as I said, take place about once a year. So in 2004, as I said, our South African Steering Committee decided to finance and build the Meerkat telescope. At that time, we had about 4.5 radio astronomers in South Africa, and our only telescope was an old 26-meter dish at an observatory called Hartbeespoort near Pretoria, which was left behind in 1976 by the NASA Deep Space program when they left South Africa because of apartheid. But we did have excellent local engineering skills. And so we decided to deviate from the accepted wisdom in the SKA international community in both how we approached and designed the Meerkat telescope as an SK precursor. We decided to run it as an engineering project. So scientists were allowed to give their views, but they weren't allowed to interfere too much. Because we believed, as some earlier speakers have said, Alex Saleh and others have said in this meeting, that for these very large instruments, you need formal engineering processes. They're industrial processes. They're not the traditional build it in our university laboratory processes. So we believed that we needed a formal system engineering process and a formal project management process. We worked with very small, very competent teams of engineers, with scientists. They worked with autonomy, but within a fairly strict system engineering management plan. At the beginning, the International SKA Consortium was quite skeptical of this whole system engineering approach, but eventually it was adopted. And it's essential in our view that you have a uniform system engineering process if you're going to run a dispersed process which is effective and efficient. I don't believe that you can manage the interfaces and manage the various codependencies and so on without that approach. So we were lucky in that we had no resident gurus. As I said, we only had 4.5 astronomers, radio astronomers. We had lots of optical astronomers, as you will have heard from Patricia Whitelock. So we used the system engineering process. So in other countries, some of the gurus had told people what we had to build, and we said, well, we don't know what we have to build. We can work out what we want the telescope to do, and then we'll do a user requirement specification, and then using system engineering processes, we'll work down to what the system should be and what the subsystems should be and so on. We decided to build a general purpose telescope, and the optimization of that design would be guided by the key science projects, but not determined by the key science projects. So we went for maximum sensitivity and dynamic range, partly in order to give us high survey speeds. At that time, there was a belief that we had to bring the cost of the SKA down by building cheap dishes. because dishes are the biggest part of the cost, and that any problems that resulted from having bad beams could be solved by algorithms. That's proved to be not true, and we in fact decided to build the best beam we could. So we eventually settled on an offset Gregorian design so that we would have an unblocked aperture. We realized that there were in fact no silver bullets to reduce costs. And the way we reduced costs was through meticulous attendance to detail and the system engineering. And we optimized the subsystems and the whole system and the construction. And we ended up being within budget and within schedule. And in fact, we got twice as much sensitivity as we'd originally specified, but at the same price. So we had a lot of international collaboration in this process. We found that the international experts were very, very cooperative and helpful. People like Steve Rawlings in particular, Bill Cotton, and of course Fred Lowe and Tony Beasley from the NRAO and many others. And people sat on our science advisory committees, on our technical review committees, on our technology projects. But some of the most valuable assistance came from informal discussions, usually late at night, after meetings of the International SKA Consortium. But we also had concrete assistance. For instance, our first LNAs were bought from the NRAO, and NRAO seconded a commissioning scientist to us. We also were very active in the Casper collaboration, which was introduced to us quite early on. That is a collaboration for astronomy signal processing and electronics research. The idea is to build signal processing hardware and firmware, which is very easily updated when new chips come out and so on. So it was started mainly by University of California at Berkeley. They built the first generation of boards, but our Meerkat team in Cape Town played a leading role and built the second and third generation boards. We also had excellent collaboration from industry. For instance, NVIDIA became very much involved with us, partly because we had such a good team that they impressed them, and partly because they were very interested in getting into the SKA program, and they saw the Meerkat as a precursor. We were also able to absorb into a kind of symbiotic relationship some South African high-tech companies, which are now producing for the international SK, such as EMSS and Parallax. They produce some of the best receivers in the world now. But the SK in general is focusing on worldwide expertise on handling and analyzing huge quantities of data which come in at very high rates. And so, of course, it's of interest to the industry, and a lot of industry has been keen to work with the SK community. The situation now in handing out industry contracts for the actual construction of the SKA is a bit unfortunate in that it's not only observing time, but also industry contracts that you get out what you put in. In other words, if you put in 14% of the funding, you'll get 14% of the contracts. That's not optimal because you sometimes have one country building something which could be done better elsewhere, but you've committed to that. So there's a picture of the core of the Meerkat telescope with the offset Gregorian configuration. There's another nice picture of the core. The whole telescope extends over 8 kilometers and has 64 dishes. So Meerkat is 64 13.5 meter diameter Gregorian offset dishes, 8 kilometers baseline. The Max Planck Institute from Germany built a set of S-band receivers because they liked the Meerkat so much. And that's been added to the L-band and UHF receivers that we'd already built. And now they're in the process of building Meerkat extension to go from the current 64 dishes to 84 dishes. and extending the baseline to 17 kilometers. And that's a collaboration between the Max Planck Institute in Germany, INAF in Italy, and the South African Radio Astronomy Observatory. There is now an SKA dish prototype on the site. So eventually there'll be a total of 197 dishes, which will incorporate the 84 from the Meerkat and the Meerkat extension, and then add the SKA dishes, which are of a very, very similar design. So we designed the Meerkat in order to be able to do commensal observing. It uses Ethernet to multicast the signal to many users. So you can do imaging, you can do beamforming, but we also have what we call user-supplied equipment, such as Breakthrough Listen, which is looking for artificial signals from the universe. There are pulsar timing, pulsar search, and transient search equipment led by Swinburne, Max Planck, Manchester, but incorporating a lot of different international collaborators. Then our observatory is also host to a number of other international projects, such as HERA, the HERA of reionization telescope, the new HIRAX project, which is being led by the University of KwaZulu-Natal in South Africa, but is international, and then various others. And there's also an optical telescope at the South African Astronomical Observatory in Sutherland called the Meerlicht, which is led by the Netherlands together with South Africa and the UK, and is slaved to the Meerkat telescope, so that you have simultaneous optical pictures of whatever the Meerkat is looking at. And the scientific program is based on open skies, so we have the best science from what we believe is an outstanding instrument. There are 8 large survey projects, one of which, the Meerkat Absorption Line Survey, is led by Neeraj Gupta from IUCA. These projects are already yielding very exciting results, as are the PI projects. We have regular calls for PI projects for about 30% of the observing time. Initially, the time allocation committee required that all projects include African scientists, but that's been relaxed now, but people are being included anyway. So one of the most important parts of the project was the Human Capital Development Program, which was based on a pipeline model. We found that in the environment of South Africa and Africa, we couldn't rely on having an adequate supply of undergraduates because we originally wanted to focus just on PhD and postdocs. But we found that we had to start at the school level and create a pipeline of young people who had come from school through first degree in physics or engineering, and then continue all the way through to postdocs. And that pipeline has been very successful. The assessment report that was done last year of the project is available from Kim de Boer or Bonita de Swart, and their emails are there on the slide. And you'll see here the grants that are given every year from that program starting in 2005. It's about 100 a year, which are given for the various levels of study. And there you'll see the distribution of the levels of study. So most of the grants are for master's, honors, and undergraduate degrees, but there are a lot of doctoral degrees, postdocs, and we also funded 6 research chairs in South African universities. But the teaching also extends to technicians and to artisans, because there's a severe shortage, certainly in South Africa, but also in the other African countries, of technicians and artisans. So this whole idea of developing African scientists and technologists was a key motivator for African participation and for our South African government. And besides the Human Capital Development Program, we also started what we call the African VLBI Network. And because these programs had been seen to be very successful, the United Kingdom's Newton Fund agreed to partner with us on a program called Development in Africa with Radio Astronomy, DARA. And DARA was very successful, so the Newton Fund then kicked in a lot more money, and so did our Department of Science and Technology. And another program was started called DARA Big Data, which goes beyond astronomy into all kinds of other areas. So the research chairs were key to developing a vibrant community in our universities, and the program has produced many junior researchers. The problem that we now face is how to get junior researchers to be mid-career researchers and then senior researchers. And obviously the postdocs, both in South Africa and internationally, play a role. Rene Klosek, if I remember correctly, was one of our initial students in the program. But a key part of it is participation in the large survey projects and the PI projects where mid-career and early career people can be mentored. We also have a graduate entry program at the South African Radio Astronomy Observatory, where if people are successful, they are then employed by the observatory. So every year, the program brings together all the PhD and MSc students and their supervisors from all the countries. We insisted on this to make them feel part of a team so they're not isolated, and also to get them used to presenting their work to their peers and senior researchers. And it's very enthusiastically attended, and we also have a lot of international leading astronomers, so it gives people an opportunity to interact with leading international researchers. So we started the African VLBI network program to repurpose redundant satellite communication dishes. We started with a 30-meter dish at Kutunzi near Accra in Ghana, and we found it was much more difficult than we'd expected. We ended up having to rebuild the whole thing, and in the process, we trained scientists, engineers, technicians, welders, and even painters in Ghana. And it hasn't been possible to continue with that program at the present time for funding reasons. But we've been able to work with particularly the universities in Botswana and Namibia, but also Madagascar, Mauritius, Ghana, and others. And Botswana and Namibia in particular have been building up quite energetic programs. The DARA and DARA Big Data programs have been very successful, and I'll show you now. This is pictures of us with Ghanaian trainees, both in Cape Town and in Kutunzi near Accra. And that's the Kutunzi 30-meter dish. And this is a diagram from Benita de Swart on the DARA Big Data program. You'll see that there have been Big Data Africa schools every year from 2017 to 2023. And there have been hackathons in all of the participating countries. And there have also been some very important virtual events, such as last year there was the Africa Women in Science, in Data Science event and hack. So that's been very successful. Unfortunately, the Newton program has either been cut in its funding or it's reprioritized, but I believe that the program's not going to continue at this point. So all of this has generated a lot of interest across the African continent in astronomy. The African Astronomical Society was launched with support from South Africa's DST, been very enthusiastic participation. Several countries are now developing smallish optical telescopes, and there are a lot of conferences and schools, and there's a lot of enthusiasm about preparing for the General Assembly of the International Astronomical Union, which will take place in Cape Town in 2024, the first time on the African continent. So one of the crucial aspects of all of this is that we've said to our colleagues in other African countries that you don't necessarily have to have a telescope in your country to be able to do radio astronomy. A lot of it you can do by accessing archival data and data that's in the public domain. But what that means is that the telescopes, whether they're optical or radio, have to have very good pipelines which produce science-ready data. But there's no longer, in my view, space for having to rely on every astronomer being an expert in how the telescope works and the data processing and all the ins and outs of that. You've got to be able to give people science-ready data, and that's not easy. But if you can't do that, it means people can't use the data and they can't publish. So we've emphasized the need for Meerkat to have a good pipeline. I believe the SK will go the same way. The other thing that's important, of course, is that the flood of data you get from Meerkat, from the SK, from all the other big telescopes now being built, more and more require the use of machine learning tools. And Michelle Lochner in South Africa has done some outstanding work on finding outliers. I'd refer you to her papers, amongst others. Then to finish off, let me just say that besides the build it and they will come, we adopted the slogan, look beyond the horizon. In other words, look at what you think needs to be done, but looks impossible at the present time. And then quoting something which may or may not have been said by Nelson Mandela, and that is that it always seems impossible until it's done. Thanks, Chair.
Thank you so much, Bernie. We can take a few questions from the panelists who are here at this moment. And we don't have much questions from the live chat in YouTube, but we can take a few questions from the people who are here. Yes, please go ahead.
Pranav, is it to me? I had raised the hand.
Yes, Professor Anpuni,
Right.
please go ahead.
Yeah. Hey. So a very nice talk as usual. I just wanted to ask the question regarding human capital. As you know, many of the countries like the India go through this difficulty in raising the number of people, number of astronomers to take up the new projects, etc. So could you just elaborate on the slide you talked about?
Sure. I would recommend also, Anupuni, that you write to Kim or Bonita and get the assessment report, which is very detailed. The problem that we had, as I say, is that our school system is fairly weak. And so we had to put maths and science teachers into the schools, particularly in the area around our telescope, and then bring young people into Bachelor of Science in physics or engineering degrees, and then take them up. So it required quite a big investment, but as I say, that was one of the big motivators for government support. And we found that we have had to be quite close to those students. So if you just give them a grant and throw them into the university, a lot of them are not able to cope with the new environment because they don't have adequate preparation from school. They don't have the cultural capital, let me call it, from home. So we've had to maintain quite a close relationship with our students at undergraduate and even at master's and PhD level. But that's been very successful. The big problem that is facing the program now, I think, is that they're producing a lot of junior researchers. The question is, how do you take them up to mid-career researchers, and then how do you take them up to senior level? So quite a lot of our students are taking postdocs either in South Africa or internationally. Some come back, some don't. Obviously, that's unavoidable. But the ones who come back are now developing quite nicely. It just, we quite honestly, within South Africa and within Africa, we don't have enough senior researchers to mentor all the more junior researchers. And that's where the international collaboration is so important through the PI programs and through the large survey projects. I don't know if that's answered your question, Anupun.
Yeah, pretty much. Thank you. This is literally, I mean, the emphasis is to, strengthen the grassroots level as well as handhold them to reach wherever you want them, right? So it's just, it's not just injecting, required things at certain levels and let them take care of it. I mean, thank you so much for this. Yeah, it helped a lot.
If I may make one more comment, because you raised an interesting point. Initially, we offered block grants to the South African universities, particularly aimed at getting young black students into the system because there were not anything like enough black students or women students. And we found that 2 of the universities were very successful and 3 of the universities said they couldn't find suitable students. And it was really a state of mind. You've got to go out and look for students and you've got to be prepared to take a bit of risk. But if you wait for people to come to you, it's not going to happen. So you've got to be very proactive in seeking out good students, and a certain amount of hand-holding is inevitable until people feel confident and are used to the systems and they're able to, for instance, basic maths and basic computer programming, we found was not a skill that everybody had. And so there had to be some support for people.
Thank you.
We can take one or two more questions if we have any. Otherwise, we'll move to Yuna. Great. Thank you, Bernard. It was a great session, very informative. And we look forward to working together while we are doing this important policy document.
Thank you.
I mean, of course, the phase 1 would be to address the kind of things that, can be addressed to the forum of G20 and Science 20. But then in extension, we would also be working with Brazil next year. And then, of course, we'll come back to you in South Africa when in 2025, you host the G20. So the lot of effort and onus will still be with South Africa. And I'm extremely delighted to say that during the entire Science 20 process, the South African Academy of Sciences have been extremely supportive. They've engaged in discussions. We've had representations from South Africa at every stage, and it's becoming more and more fruitful kind of partnership. Now we have Yuna Collema. She's the director of the Canadian Institute of Theoretical Astrophysics. And she would be talking about the pioneering panotopic spectroscopy. We're really, really looking forward to your talk, and I will not hold neither our audience or us from listening to you. Yuna.
Well, thank you so much for having me here at this exciting session. That was a wonderful introduction. I'll be talking about the Sloan Digital Sky Survey, the 5th phase, and it's called Pioneering Panoptic Spectroscopy. And you can just see a little preview here in the video of the type of instrumentation that we're developing for SDSS-5. And I do just want to thank the organizers so much again for inviting me to speak at this exciting event and forum. So what is SDSS-5? So we are focused on all-sky time domain spectroscopy. So you've heard yesterday sessions about time domain imaging. SDSS, of course, pioneered astronomical sky surveys, digital sky surveys, which is, of course, what we all use now. And the sort of state of the art are these imaging surveys. And in SDSS, we always try to push the boundary. And so in SDSS-5, we are doing time domain spectroscopy. But what is SDSS? So SDSS has 4 fundamental components. We are a science survey. There are 3 mapper components. We are a dual hemisphere observing facility. So there's telescopes and instruments and software associated with that observing facility. We are a global consortium of partner institutions. And the most important thing is we're a collaboration of people. So I mean, we are really while SDSS was one of the biggest surveys and the biggest projects in the 90s, we are really a grassroots global consortium and collaboration. So it's really a counterpoint to some of these mega projects that you've been hearing about. So this is really as big as a project can be while remaining strictly scientific and rational. And I love that that quote from our last speaker, Bernie Farinoff, because that's just something I think is a really great thing that we're able to preserve at the scale of SDSS, which is, of course, not a mega project with international treaties. We have international agreements, but I really like this, and that's because I'm a theorist. So and SDSS has a tradition of theory-driven experiments. So all of the previous leaders of SDSS have had some theoretical bent, and I think that's a really important distinction of SDSS compared to more sort of discovery-focused type of projects, because we're always putting in maximum capability, but trying to make sure that we are actually testing theories of the universe, and that's something that I think guides a lot of our thinking in the project. So like I said, we are a global consortium, so there are over 70 institutions spanning 5 continents. Unfortunately, we do not yet have any members from India. We would love to welcome you into the collaboration, so please do consider reaching out to me after this talk. And if you like what you hear, please consider joining us. There are a lot of spectroscopic surveys sort of on the market. This shows the projection of spectroscopic survey facilities to 2020. These were things that people had planned back in 2017 and 2018, and there's many different experiments, some of which are on sky, some of which will almost be on sky. What is unique about SDSS-5 is that we are both optical and infrared. We are on all sky facility, and we are a multi-epoch facility. So we do multiple epochs of spectroscopy. The only thing that is sort of similar to that is the Gaia project, which is in a very, very different regime in terms of what it is actually observing and what its mission is. What are the key questions that drive SDSS-5? So we have these 3 mapper programs, and we are fundamentally interested in the structure, order, and multiplicity of stars, so stellar astrophysics, as well as the use of stars as a probe of the galaxy. Black holes at all mass scales, and in particular, we want to understand what the mass and spin functions of black holes are and how they get their mass. So how do black holes go from being a solar mass all the way up to being a billion solar masses? And galaxies, we really want to understand how galaxies work in terms of how in the context of Lambda CDM, our current cosmological model, we don't want to just have plausible explanations that are degenerate theoretically, but we actually want to constrain some of these theoretical predictions by looking at how energy and mass is cycled in the interstellar medium, and that gives rise to our local volume mapper. So we have three mappers. The Milky Way mapper is going to be looking at, or is currently looking at, over 6 million stars in the galaxy. The black hole mapper is looking at over 500,000 supermassive black holes and stellar mass black holes. And our local volume mapper is an integral field unit spectrograph facility, and so the number of spectra there is very, very high, and it's looking at the large swaths of the Milky Way and nearby galaxies. So I'm going to just go through some of the science drivers for each of these mapper programs to give you a flavor for the program. So the Milky Way mapper has core programs looking at white dwarfs, looking at the solar neighborhood, looking at young stars. And these are, because the Milky Way mapper is focused on stars, we think about our program even from the structure and evolution of stars. So we have these core programs that are central to the project. The Galactic Genesis project is a program that is mapping, basically using stars like clocks, and I'll discuss that in a minute. We also have programs focused on RV variability, the types of stars that host planets, trying to characterize those stars, looking at compact binaries, dust production within the Milky Way, as well as seismology on the red giant branch, astroseismology being one of the most exciting developments in stellar astrophysics over the last decade. And then we also have extra fibers, these open fiber programs, and I'll describe the hardware in a minute, but these allow us to look at halo stars and stars within the Magellanic Clouds and cluster stars. And then, of course, there's standard calibrations in the program. But the thing I think that is fundamental is getting a spectroscopic age map of the Milky Way using the Apogee instrument, which I'll describe in a minute. In 2016, we were able to use early machine learning and deep learning techniques to extract ages for thousands and thousands of red giant stars from beyond the galactic center to the outer disk. This was a real advance. It was one of the first indications that machine learning could be extremely important for astronomy. And what's nice about this problem is that it's very much in the intuitive or interpretable territory of these algorithms. So we understand why they're working, we understand what they're doing, and so it makes them extremely powerful. And so as a theorist, when we're predicting the formation of a galaxy, one of our most robust predictions is the time that stars are forming within that galaxy. The Milky Way mapper, by providing spectroscopic ages, not for tens of thousands of objects, but for millions of objects, now is going to give us a very high fidelity map, age map of the Milky Way galaxy, and allows us to do galactic archaeology in a whole different way. And just the existence of these stellar ages really changes how we can look at the HR diagram, how we can look at the structure and evolution of stars, because time is that fundamental parameter that we need to anchor our theories. And so having that is critical. So we're looking all across the HR diagram, and I'm just showing that here. We go from stellar candles to cinders, as we like to say. This is new in SDSS, so typically SDSS focused only on a very narrow region of the HR diagram. In SDSS 5, we are doing the whole thing, so really trying to understand stars using this time domain spectroscopy to understand how they evolve over time. Just to give you a sense of how sensitive SDSS5 is to companions, because one of our drivers with the time domain, you get to see variability, and variability gets to, reveals companions and binarity. if we look at the separation versus the secondary mass that we can detect for a normal stellar companion, with SDSS-5, we go all the way down at a very broad range of separations here on the x-axis, down to the planet mass category. So we can, of course, we see black hole binaries, of course, we see neutron star binaries, we see white dwarfs. They make a huge signal in the radial velocity, but we're actually going down to those Jupiter mass planets, even at pretty significant separations. And so this is a very exciting aspect of doing time domain astronomy. You get all of that binarity, which is critical not just for stellar evolution, but also, as we know, for planet formation and evolution. SDSS has access to infrared and optical spectra, and at high and low resolution, which gives us access to this variety of elements. And so what I'm just showing here is just what our precision is on these various elements in the periodic table. And of course, you've got your alpha capture elements, your light elements, and your iron peak elements. So really capturing a lot of critical phases of nucleosynthesis. Our black hole mapper is primarily in the optical. Our black hole mapper is really aimed at understanding how black holes grow and evolve with time. And I would say the key thing about the black hole mapper is that we're getting masses. So we have three basic components to our black hole mapper: reverberation mapping, looking at light echoes to measure black hole masses. We're also looking at time domain black hole accretion. These are these changing look quasars, and I'll show an example of that in a minute. And here you can see a spectrum, a changing look quasar, where the actual broad and narrow emission line regions of the AGN are coming and going on short timescales. Quasars are known to be variable since their discovery, but actually understanding how the black hole environment is changing spectroscopically allows us to pin down some critical accretion questions for black holes. And of course, we have a very large program following up the newly launched eROSITA facility, where we're measuring X-ray properties. The eROSITA facility is providing that X-ray data, and we're providing optical follow-up of those sources. So just to give you a sense of the sky coverage, the eROSITA, and this is in collaboration with the Max Planck Institute for Extraterrestrial Physics, is providing the southern sky, and the reverberation mapping and changing look fields are shown in the bottom. Just to give you an example, we have transient changing look AGN. So the opening up the time domain opens up all sorts of physics that, we're not just looking at steady state anymore. We're able to look at transitions, we're able to look at transients, and understand, well, how is this whole structure, how is the structure of the broadline region around black holes, how is this formed, and how is it evolving over time? And this is a recent paper from SDSS, the SDSS collaboration on a particularly interesting changing look AGN that's changed over very short time scales. Our local volume mapper is something new entirely. So instead of building gigantic telescopes, we build really amazing instruments to go behind really small telescopes. So these are tiny telescopes. It's an array of 4 telescopes with 3 very, very powerful spectrographs and gigantic IFU, integral field unit, in front of it, in order to do resolved spectroscopy. And you can see in the background of this image the size of our IFU on the sky. You see it's about the size of the full moon, and there's about 2,000 fibers in this system. I like to say, subgrid is very 2010s. So what I mean by that is often our physical prescriptions are what we call subgrid, below the grid that we're actually resolving in our theoretical calculations. We need to change this because we want to test physics at that level, and that's where all of our degeneracies lie. So in order to actually constrain these models, we have to go to these scales observationally. So this is an image. This is an image of a star forming region, and you can actually see here in yellow, I've just overlaid positions of stars that we're getting from our other mapper programs. And now, instead of just looking at the sort of very broadband imaging data, we will get a spectrum at every spaxel here in this image. So now we are not just looking at things sort of in time. Here, we're really resolving things spatially so that we can trace out these structures spectroscopically. And we all know that the physics is in the spectra, and so that's where we have to go. So you get the effective temperature, luminosity, metallicity, ionization fraction, age, for all of these for the stars and gas in your field. And just to give you a sense of what that looks like, if you look at kind of a smeared out version of an H2 region, it's very difficult to, and on the left here where you've got, 100 parsec per pixel resolution, very difficult to disentangle what's actually happening there as we go to the right, where we start to get to that 1 parsec per pixel scale. You can start to see things breaking up. You can start to see the shocks. You can start to see the individual stars. This is really critical because we have a lot of different physical processes that could be operating under the grid. And so by actually resolving this out, we're testing this directly, and we'll just get much higher fidelity information about the physics of star formation and the physics of star formation feedback in galaxies. Just to give you a sense of the survey extent, it's a very simple selection function. You can see we have a deep field there in purple. We're also looking at the clouds with this IFU. So now you have to think there's 10 million spectra here contiguously packed. So it's a pretty intense data set. And of course, there's an H alpha map in the background there. How are we doing this? I think one of the key things that's a theme of this meeting is just the incredible ingenuity, engineering, astroengineering capabilities of humanity. So we are going from the traditional SDSS plate system to robots. So we have replaced our focal plane with robotic fiber positioners. So instead of having to plug a fiber into a big metal plate, you now have a robot that can position a fiber incredibly accurately to any position in the sky, and these robots all overlap. That allows us to get this contiguous density that we need to actually deliver on some of the science I was discussing. So the legacy hardware of SDSS, so we had 2 optical spectrographs. They each had 1,000 fibers at a resolution of around 2,000. And we had 2 apogee spectrographs, one in the northern hemisphere at the SDSS telescope, shown in the upper left, with 300 fibers at a resolution of 22,000 operating in the H band. And we had small IFUs with 127 fibers per IFU. And of course, in the southern hemisphere, we had a copy of the apogee spectrograph. So now we've made a new Y-field corrector for the northern telescope to make the focal plane telecentric, and that corrector, so the SDSS telescope now takes the best images that it's already taken. We've built these 2 robotic fiber positioning systems to simultaneously feed the optical and infrared spectrographs. We have we've upgraded the infrared spectrographs for improved radial velocity accuracy, and we've put octagonal fibers and Fabry-Perot interferometer in order to achieve an RV precision of 30 meters a second. That gets us to those brown dwarfs and planets that I was showing earlier. And we've improved the electronics and the fiber slit heads for the BOSS spectrographs, and we've moved one of those optical spectrographs to the southern hemisphere. There's a lot of equipment to be built. And in addition to this, we built this new observing facility for the local volume mapper. That's the IFU facility. So these are 4 small telescopes with a large IFU attached to 3 DESI copy spectrographs. These are spectrographs that are copies of the ones used in the dark energy survey instrument. So this is a pretty intense building procedure. And of course, we all know the global pandemic hit right as we were building all of this, but the incredible resilience and dedication of our team meant that we kept going. So you can see our corrector there in the lab with the Johns Hopkins team. Our robotic fiber positioners are now fully deployed in both hemispheres, and so you can see our small commissioning team in the bottom right there. It's Rick Poggi, Connor Sayers, and Jose Sanchez Gallego. I was behind the camera there taking the picture. And you can see our robots lit up from the back here in the focal plane. On the left-hand side, you can see the extent to which astronomers go to check their interfaces. And so our systems engineer built a model FPS out of cardboard in her driveway. That's Stephanie Wachter, in order to test that all of our fiber routing was going to work, because of course we had restrictions about going into the lab. The robots are working great, and so I'm just going to show a little video where you can see them slithering around. You have to imagine these are now on sky and targeting stars and black holes and galaxies. And of course, that's the algorithm that we use is shown on the left-hand side. That's written up in Sayers et al. To actually make sure that none of these robots collide into one another. And so that was all homegrown equipment, all homegrown software. And I think that's something that is really special about this collaboration and this project, is that we can do these tremendous things, these cutting edge things, by small groups working together, as opposed to some of the mega projects which have different operations. And so you can see, looking at SDSS 1 to 4, you see that plug plate pattern. It takes time to drill those plates and plug them and put them on the sky. So you could only do 7 fields, 8 fields a night. Now with SDSS 5, we can be contiguously observing the sky. So it's just an incredible leap in what our capability is on the telescope. We are starting to make our first discoveries. There's been, now this number is out of date, there's hundreds of projects announced. This is from an early paper by a student, Vedant Chandra, a 99-minute double-line white dwarf binary, which is one of the exciting programs, exciting objects that we have already discovered. And so we are currently on sky, taking data from both hemispheres with our robotic fiber positioning system for the black hole mapper and the Milky Way mapper, and our local volume mapper, which is a lot more hardware. This is showing it through the years, because we built that new observing facility over the pandemic, as well as all of this hardware. And you can see our recent meeting that is currently being commissioned in the Southern Hemisphere. So that is all built, all installed, and you can see again, I believe that is Jose Sanchez Gallego in the, actually that might be Tobias Feiger, I'm not positive, but you can see our commissioning team. This is from Tom Herp's group at the Max Planck Institute for Astronomy in Heidelberg. You can see them commissioning earlier in February. So we are getting ready for first science observations with this IFU. So this is an incredibly exciting amount of hardware to build, with the science discoveries now just starting. Now to the point of, I think, the broader themes here, one of the things that makes SDSS work without treaties and that kind of thing is that it has well-defined policies for membership and collaboration. So we have principles of operation, there's a publication policy, there's a code of conduct, there's an external collaboration policy. We honor these policies. So there's no cordoning off the science, nobody gets any special preference. Members are members are members. It doesn't matter what country they're from or where, what institution they are at. We support early career scientists become leaders. Many people who have worked in SDSS at various levels have then have gotten that experience to lead those mega projects that we've heard about. And as the SDSS 5 director, My goal is to maximize the scientific self-actualization for members of the collaboration and beyond. And I think that's something that that is really critical for leadership to embrace is, how do you get not just the best science out of your project, but how do you enable the people, the human element? How do you enable them to feel rewarded and not just feel that way, to be rewarded and to be fulfilled working on the project. Of course, in every SDSS, we have a lot of people who work very, very hard to make these sort of outrageous plans reality. And so I'm just showing the SDSS 5 org chart here. As a community, and we've heard this throughout the sessions, we really need not just a robust pipeline of these individuals, but we need a rich future for these individuals. We hear about workforce issues because, well, the allure of working at a company and making a lot of money is very attractive. But I do think that these projects offer something better than money in many respects. But I think we have to ensure that these individuals have such excellent training and such excellent opportunity to innovate that they don't have to worry about employment and those things that many of us have had to worry about in the past. And just ending here, we can actually map all the galaxies. So this is a figure of Milky Way-like galaxies that projects like SDSS and now the Dark Energy Spectroscopic Instrument, DESI project is mapping. You can see over time how we have been basically staying on a Moore's law of galaxy redshifts. And with the current sort of generation of facilities, we will continue on this line. And if we stay on this line, which is going to be very difficult to do, we can map all of the galaxies, all the big galaxies by 2060, which is really a tremendous thing to think about. And to that point, we've been thinking about, well, we've got these robotic fiber positioning systems, we have these robotic focal planes, the SDSS and DuPont telescopes are 2.5 meters in diameter, but what could we do with a very wide field 6.5 meter telescope? Well, we could actually stay on that line and we could pack 26,000 fiber robots into that focal plane instead of 500. We could feed many DESI spectrographs instead of just the few that we're feeding now. And we could, in principle, overlap with the Rubin telescope and have spectroscopic complementarity to that facility. So very exciting concept. The megamapper's in a conceptual design phase right now. And I just, you got to pause for a second because you can build these machines to collect data way faster than you can digest and understand the data. And that's just, it takes a lot more time to do the scientific work than it does to do some of the engineering work at some level, which is remarkable given the amazing engineering that goes into these projects. And so I like to say, if you love your data, set it free. And we heard yesterday, SDSS has been the industry leader in making data not just publicly available, but also usable. There have been over 11,000 publications using SDSS data. And the most interesting aspect of that number is not the total amplitude of that number, but the vast majority of those publications have been from outside of the collaboration. And that shows you that you don't just have a collaboration that's really productive, that you're actually enabling a vast array of other stakeholders outside of the collaboration who maybe aren't at institutions that can afford to join the collaboration. I want to emphasize there's no long-term home for these data. This is a huge issue with the spectroscopic survey facilities. While we are working as a collaboration, we can serve the data. But if there's no SDSS 6 and there's never a guarantee for another SDSS iteration, there's no institutional entity that has the mandate to curate these data for the long term. This is an absolutely essential thing to fix. It would be criminal to have taken all of this data and to not have some type of archive for the long term for these. This would be something that would be a real shame and a real waste. I sail, and so SDSS 5 has been an incredibly fun and fast ride. The Mega Mapper looks like something like this, and so I just want to end with this quote by Robert Oppenheimer. I think this is something that's more important now than maybe ever before. We really need to get together as a global community on many of these issues. Our Galileo moment is right now. We have these electrical, optical, quantum revolutions that have given us this incredible ability to acquire and analyze vastly more data on vastly more scales, time scales, spatial scales than previously, all across all wavelengths, and not even just wavelengths, but also gravitational waves. We've observed a huge amount, and as I showed in that MegaMapper graph, we could soon observe all the galaxies and all the other stuff, but only if we are able to work together as a species. And so with that, I will just say, please consider joining SDSS, but you are needed wherever you are, whatever you do. So thank you very much.
Thank you so much. It was a fantastic talk. We open the floor for questions.
Can I go, Pranav?
Yeah, please go ahead.
Yeah. Hi. So again, very thrilling talk. I mean, it is very impressive what SGS has done. I'll go back to the early part of your talk where you sort of emphasized, and also later, that this is different from mega science projects. I would like to know what specific things you have in mind. That's because, do you look at it like, we have collaborations within, groups, which is what astronomy has always seen, and that has grown. So do you see SDSS kind of things as a stepping stone towards mega sciences, or a completely different paradigm of global cooperation?
I see it as both. So it is a completely different paradigm of global cooperation in that it's really small scale science, and there's no treaties. I mean, many of the mega things that we see, they're so impressive, and they require such coordination, and they require government coordination at a very high level. And as Bernie mentioned in his talk, that means a lot of political mobilization and political decisions that maybe aren't the most rational or scientific decisions, but those decisions. Well, in SDSS 5, we don't have that kind of support, and we don't have that kind of those kinds of strings. So we are supported by the National Science Foundation through their mid-scale infrastructure program, but we're not a treaty level project. So it means that you get you make decisions based on what makes sense. So it is also the case, however, that in the mega projects, you need sensible decision makers. And so where do you get that experience? And so some people, when they're in SDSS, they love working at a scale where their decisions are just translated directly into the action, and their contributions to that conversation are it's really done in a sort of scientific way and a rational way. Okay, these decisions are made in this way. Other people get the taste for doing something huge and want to do something huger, more huge than you can do with groups maybe coordinated the way we're coordinated. So I do think that there's a certain scale, and in particular it's a funding scale fundamentally, because universities are able to work together collaboratively to do tremendous things. But if you want to do those billion-dollar, multi-billion-dollar experiments, that's a different type of entity, typically with university stakeholders, but it's a different entity. And so I think SDSS is both a different paradigm of working, but I think it's also a training ground for doing next generation things, and that's in the project management, in the systems engineering, in the software engineering, in the hardware development. Like there's you know, if you're working on an instrument for a space telescope or a you know, a giant telescope, you know, the aspects that you're contributing to are much smaller. You're part of a much bigger machine than when you're working on these smaller scale projects. But how do you get the training to do that? And some people like to do things end to end. They love that systems level kind of mastery. Other people love that deep dive where they can contribute a very deep knowledge. I think that it's important that we have, you know, I'm originally trained as a cosmologist, so I always think about the power spectrum of structure. And although I'm sure that many of the radio astronomers also think about that as well, I think it's really important that we have a fully populated power spectrum of projects that people can be part of. What I worry about is that some of the smaller scale projects will get basically eviscerated by the mega projects. And I think that would be very unhealthy for the field and for the mega projects themselves, actually.
Thank you. Yeah. So maybe we should move on. I'll have more questions. Maybe I'll get in touch with you offline.
Yeah, please do. I see Bernie's hands raised.
Bernie, you
Ask
have
a question.
Yeah, please go ahead.
Thank you. You know, you raised an issue which I think is fundamental, and that is that there's such a huge volume of very exciting data coming out now, and it's going to be even more in the future. So I'm very jealous of the young astronomers who've got these wonderful opportunities, but it raises the problem that you mentioned, which is that the volume is so huge and the rate is so huge that people don't have time to actually think about what they're doing. So every time I used to walk into our offices, I would see everybody crouched over their computers and very busy data processing. And I'd say to them, well, when do you get time to actually, why don't you get a flip chart and just sit down and think about it? And of course, the first answer was, what's a flip chart? They'd never heard of such a thing. But it's a more serious problem, which is, I think, driven partly by the fact that all these people depend on soft money. So you get a grant, you do a project, you don't really have time to dwell on that project because you've got to be applying for your next grant, otherwise you haven't got a job. Can you comment on that issue of soft money and the lack of tenured positions?
Yes. So first of all, I think it is critical that we have think time. I think think time is something that we need as a global society generally. I think that the digital revolution has been remarkable. I love my machines so much, especially when they're computing with me. But we actually do need to touch grass and to actually reflect, because there's also sort of processing that has to happen. More than just raw digital processing. So that's just an incredibly important, I would say, sociological piece that I think leadership should be active on. So flip charts, the more analog, the better in that sense. So I've just designed a state-of-the-art facility, and it fundamentally features blackboards. So I'm pro analog equipment. But I also will say that to the issue of soft money, I think that we are trying to use the existing institutional framework that we have to do these bigger and bigger things, and we need new institutional frameworks. So when I say that there's a rich future that a lot of these infrastructure developers should be looking toward, there has to be a richer landscape of opportunities in terms of institutions that people can join. Not being a professor is not for everybody. And being, not everyone is the best mentor. Not everyone is the best, researcher. We have to more properly honor the variety and appreciate the variety of skills that people have, and provide different educational and institutional entities to actually absorb and liberate people. at CETA, and I'll just put my CETA director hat on for a minute, we have these incredibly brilliant scientists, these young scholars who are at different student or postdoc phases in their careers. They're terrified for the future. And that's worrisome because their future is so bright, they're so capable, but the reality of the way academic research has been structured is that there isn't this rich variety of institutions the way there is, for example, in industry. Industry, I think we could learn something. I think academia could learn a lot from the sort of different types of companies and different types of entities that exist in the corporate world. We could do more than just research institutes and universities. Like we really have a pretty limited medieval view here, and I think we can update that in this century, and I hope that we do, because I think there's a lot of different pathways that we know from Feynman. There's a lot of different pathways that can be taken, and we want to make sure that people, or when I say self-actualization, I really mean it in the sense of people should feel proud of their skills and their abilities, and not feel like, oh, I have to become a professor or a research scientist, or they shouldn't feel so or I have to leave the field, leave astronomy and go into industry, and that could be banking, or that could be there's just a much richer industrial capacity than there is an academic capacity. And I think we have to ask ourselves if that balance is right, and if we're doing our part on the academic side to to support these. The soft money people, I mean, many of them are, they're going to be funded again and again and again because they're so excellent, but they have to be stressed out every 5 years. Why are we doing that to people? So I think that we have to identify these. I think we have to actually come up with real structures that relieve these unnecessary self-inflicted pain points. And of course, budget realities are budget realities. So that's always the case. But we don't have a tradition of mobility in astronomy. We don't have a tradition of, really being able to move from institution to institution, right? Faculty stay often where they are for many, many years. So I think we need to revisit our structures and generate new ones.
Thank you.
And if we don't have any more questions that are directed to the speaker, we can move forward and begin with our panel. I'll just wait for a moment if anybody has any questions. If not, then we'll just go ahead. Shall we go ahead?
Sure.
Yeah.
Perfect.
Great.
Great.
Thank you, Pranav.
My pleasure. Thank you so much for this wonderful talk. And I have a few questions that I will get in touch for offline after while we are working on the policy document. Thank you so much, speakers, for joining us for the Regional Global Collaborations panel. For the panel, we have Annapurni Subramaniam, Bernie Faneroff, who you've just listened, Ishwar Reddy, Jessica McIver, Kazuhiro Sekiguchi, R. Shrianand, Ronaldo Rosa, Stefano Anderon, and Tarun Saurodeep, who will be discussing perspectives, ideas, and the key questions that are central to the regional or global collaborations model. I would like to invite the panel moderator, Jess, to kindly take the lead and take it forward.
Thank you very much. Good morning, everyone. Thank you for joining, and thank you for all of our panelists for being here. So we're going to be building on the talks by Bernie and Juna, and we're going to start off with a round of introductions. So I'll kick us off. So hello, I'm Jess McIver. I'm an assistant professor at the University of British Columbia in Canada and the deputy spokesperson for the LAGRO Scientific Collaboration, which Juna might rank as a mega project. There are 1,400 of us in 19 different countries. So I'm coming from that perspective. And then let's see, how about Annapuri Subramaniam? Please go ahead and introduce yourself.
Hi everyone, I'm Annapurni Subramaniam. I am the director of the Indian Institute of Astrophysics. I'm an astronomer. I work on stellar star clusters and stellar evolution of the nearby galaxies. The institute actually has a lot of observatories on the ground in India, and we also have a couple of, one of the space observatory like the AstroSat, one of the telescope UVIT is integrated by the institute, and we also going to have an instrument to be flown to the L1 point as part of the Aditya L1 mission. Thank you. I look forward to the discussion.
Yes, me too. Thank you. So next up, we have Kazuhiro Sekiguchi. Please go ahead.
I'm Kaz Sekiguchi. I'm at the National Institute of Natural Sciences and the Astronomical Observatory of Japan. I just retired from NAOJ this March and joined National Institute of Natural Sciences, which is the parent organization of NAOJ. So I still be at the National Astronomical Observatory of Japan. And I'm a organizer, APRIM, Asian Pacific regional meeting of IAU next month. And I'm organizing this regional collaboration session. So if you are interested in, you can join by, you can come or you can join via internet. So
Very nice. Thanks for sharing. All right, next up we have Raghunathan Srianand.
Hello, good morning and good evening. I am Srianand. By profession, I am a spectroscopist interested in cosmological issues. And at present, I am heading an institute called Inter-University Center for Astronomy and Astrophysics, in short, IUCA in Pune. We are a small institute, but contributing to all national and international projects in which India is involved. In addition, as an institute, we are part of SALT collaboration. We are leading one of the key science projects of MIRCAT. We are also in LSST and HIRAX experiments. Our faculty members participate. So it is like a regular research institute. But I would like to highlight uniqueness of this institute because its institute is constituted to support research in astronomy, astrophysics in university sector. There is a big difference between universities in US and universities in India. In universities in India are mainly focusing on education because of lack of resources. The research component is very much lacking. So IUCA was set up as a center where university teachers can come and spend their time during their non-teaching days and carry out the research. And we support all the necessary things, necessary observing time, computing resources, etc., to support this activity. Just to give a number, there are about 230 PhD researchers, guides, or professors across the country who come and spend time in IUCA. And typically, we support about 200 PhD students across the university who can come and spend. This is a very unique setup because this allows people from even remote universities to get into very high level of astronomy research. Thank you.
Yes, excellent. Thank you for sharing that. And then next up we have Stefano Andrean.
Can't hear you.
Stefano, we can't hear you.
No, we can't hear you.
We can't hear you.
All right, very good. So we'll go from Stefano. We'll come back to you, Stefano. I'll move next to Tarun Soradeep. Please go ahead.
Hi, I'm Tarun Soradeep. I'm a cosmologist working largely in the cosmic microwave background on my life. I'm currently the director of Raman Research Institute, but I'm on leave of deputation from IUCA. Sri Anand very nicely described that institute. I am relevant to this panel largely because of my kind of experience in being in this whole Indian group in the Planck collaboration, which was a CMB mission, and also been very, deeply involved in leading the effort to, conceptualize the LIGO India project, and have played various roles leading up to its, recent approval, full budgetary approval. Thanks.
Yes, and congratulations to you on that.
Thanks.
Wonderful
Yeah.
news. All right, I think I'd like to go next to Bernie Fanaroff. So we've already heard from Bernie as part of his talk before, but Bernie, would you like to introduce yourself again to someone who may be just joining the call?
Sure. I did a PhD at Melbourne Law, Cambridge from 1970 to the beginning of 74. And I taught for a year and a half at the University of Witwatersrand in South Africa. And I left astronomy for 27 years. I only came back when I was asked to lead South Africa's Blenford Square Kilometre Array Telescope, and then we got the Meerkat Telescope as well, and we started the Human Capital Program, the African BLBI network, and so on. And then I retired at the end of 2015. So I have no formal positions after that in astronomy.
Very nice.
Yeah.
All right, and then finally, let's check back in with Stefano. How's it going, Stefano? All right, so Stefano's still working on it. So we'll come back to you, Stefano. And if you've got answers for us, then please also feel free to use the chat window on YouTube, and that's a nice place to plug in. So Juna asks, you're very welcome to join us, Juna. Would you like to say a couple of words about your background for somebody just joining the stream?
So my name is Juna Kohlmeyer. I am the director of the Canadian Institute for Theoretical Astrophysics and a professor of physics and a professor of astronomy and astrophysics at the University of Toronto. I'm also the director of the Sloan Digital Sky Survey, fifth phase, SDSS 5. And my background is I'm a theorist and a kind of breed of generalist in theoretical astrophysics. So I work on a broad range of theoretical questions from planet formation and dust all the way up to cosmology.
Glad to have you with us. That'll bring a great perspective. All right, so I'd like to jump right into the first question. So first up, how does regional and global astronomy collaboration benefit the sustainable development of the world? And I'd like to get us started with a few slides from Kaz Sekiguchi, who will kick us off in an answer to this question. Please go ahead, Kaz.
So can I just share my slide? Yeah, coming. I just hold on and I have to slides. Slideshow. Well, this is very limited, and well, my intention is just to, for discussion's sake, need to throw in some idea. So it's very limited idea, very incomplete one. so you can fill in a lot. So I was thinking about what we can do for sustainable development of the world. And you probably heard from Vanessa's presentation earlier today, and she actually explained so many interesting things. And I just itemized some of those, that like data sharing and knowledge exchange, and access to some diverse expertise of some institutes, and the training and the capacity building, and global networking, and technological advancements and innovation, public engagement and outreach, and addressing global challenges. So I only show two viewers. So you can come up some other things, but it's very difficult to somehow directly astronomy contribute to the world sustainable development. But SDGs, the relationship with astronomy, you probably see that the Vanessa's presentation. And I got one thing to add. That something is addressing these global challenges. And we can actually using astronomy data, those big astronomy data, and contributing the climate change and the space debris monitoring and the planetary defense. And these things may be quite interesting for those G20 country politicians. So I just throw into these items. So please give me more your thoughts and more your ideas.
That's a great opener. Thank you very much, Kaz. So next I'd like to go to Bernie. If you'd like to follow that up, please go ahead.
Thank you. I think there are a number of areas that are very important. Vanessa spoke about the IAU's work on using astronomy for development led by Kevin Governor, which is doing good work. But let me take some other issues. The first one is a state of mind. When we first became involved in the SKA project, there was a very strong view from other countries, but also within South Africa, that we shouldn't be spending money on something esoteric like astronomy. Being in the Southern Hemisphere, we should rather be spending our money on developing drought-resistant food and water issues, and why are we wasting money on something esoteric? And the attitude that we took, and which our government supported, was that we are already assigned to a second-rate world where we export raw materials and they're made into Apple iPhones, and then we buy the Apple iPhones back, and we don't really want to stay like that forever. If the global south is going to advance, it's got to develop science and technology capacity and capabilities and expertise. So we had to really change people's minds, both internationally and within Africa, that this was possible. Obviously, it's not a linear process, and it's a case of 2 steps forward and 1.5 steps backwards. But there is progress, and there is recognition increasingly that we have to put resources into research. One of the advantages of astronomy, particularly radio astronomy, is the skills that young people are learning, very generic skills in data science, in digital signal processing, in machine learning, and so on. So they're not skills which are confined to astronomy. You can, as Jim was saying earlier, you can go out into the economy with those skills. And that's why there's been a lot of support for the Data Big Data program. Anna Scaife, who's now at the Turing Institute in the UK, is the driving force in that program. And I would really recommend people speak to her about her experience, or Bonita de Swart in Cape Town, who ran it with Anna. But that was a very important question, the recognition that for sustainable development, you cannot continue to be second-rate countries which are exporters of raw materials and recipients of manufactured goods. And of course, there's the practical issues, which is that you need to develop institutional capacity in those countries which can support the ongoing development of expertise and skills. And that's a very difficult one to say. In Ghana, for instance, the deal that we had with them to build African BLDI network telescope in Katunzi was that we would supply the infrastructure funding and they would supply the operational funding. They really struggled to do that. Botswana and Namibia have been much more consistent. They have a lot of effort and quite a lot of resources into the universities and into developing those skills. So I think from the question of sustainable development, it's not just a question of climate change and developing drought-resistant plants. It's also developing the capabilities and the expertise in the global south. That not necessarily to compete with the North, but to be able to be on equal terms with the North. Thank you.
Thank you, Bernie. Those are really important points. And next, let's please go to Juna.
I think that one of the advantages of astronomy is, first of all, it's the experiment that unfolds in front of everybody's eyes in the world. So it's fundamentally global in a way that other areas of science are more local, and it's and so it's a great access point for actually bringing forward educational materials, bringing forward math and science literacy. Mathematical literacy is one of the most critical elements of future development, and many places and rural communities and even urban communities lack mathematical literacy among children. This is a very serious global issue, and astronomy, being both very exciting but also highly mathematical, provides a really great access point for people. So I do think that that aspect of sustainability comes in very naturally within astronomy, and I also feel that that the necessity of doing these grand projects, just the difficulty of doing the types of science that we are trying to do in astrophysics, the challenge, and I think particle physics has a similar challenge, means that it's just fundamentally global and international tradition, and I think that's just an important boundary condition for the for that development. So in terms of why astronomy matters for the global development, you might think, well, banking or some other sector is critical, but astronomy is fundamentally global. And I think the other really important aspect is, you can't make a lot of money on astronomy. So we were able to set the SDSS data free because there was no profit motive that another entity had to keep it secret. So we're not an oil company or a space company where there's a real profit motive to keep our data secret. And that is something I think is a bit ascetic of, of the astronomers, but, that's why we wear the robes. Just kidding. Astronomers don't really look like Merlin anymore.
Only on graduation day. All right, well, thank you all for your thoughts. So I'd like to move us on to a few more questions before the end of our hour here. So the next question, what do you see as the biggest challenges to truly global collaborations in astronomy? And I'd like for Tarun to please get us started.
Right. So we had an interesting panel discussion yesterday on large projects, and some of the obvious challenges were talked about. Some of them have covered in the talks here also. So I would like to focus on something which may not be as obvious. One is this need to be seeking out cooperative models. I mean, that is something that needs to be in our, DNA. And astronomy, as Juna nicely pointed out, is a universal science. We should really capitalize on that and create a mechanism by which it's easy to set up collaborations and small collaborations, which can then fructify into moving to bigger ones. And it's very important to have a long-term vision when we say we want to cooperate between A and B. And again, Bernie made a very nice comment as to why invest in South Africa or ask South Africa to invest. That's because, in the long term, you will win out in this collaboration because, and that I think is something which also I realized in this whole experience with LIGO India when we first started talking to people about, India getting into experimental science. We're just a bunch of few people who were, I was largely interested, and there were a bunch of experimentals. The very fact that there was a global welcome to see India come through and get this going, I think is very important. So we should be seeking to set up collaborations with a long-term vision, because I think over a couple of decades, I'm very sure the whole idea would look much more attractive than it may have looked earlier. And there are people with a lot of concerns even now. So I think that it should be a long-term vision if you want to cooperate, and you need to set up mechanisms which, like neurons, sort of seek out synapses. So that there should be models where people should be talking to each other across the globe in meetings. So kind of making that much more simpler would be a very good way forward. We don't have that for countries like India to the extent that we would like to. Thanks. I'll let others speak on this.
Yeah, thank you, Taran. Excellent points. And I'd like to go next to Sri Anand. Please go ahead.
I just have two points to make. One is related to small collaborations, in the sense that we don't have large investment, but we want to have collaborations across countries. And I'm talking from a developing country like India in this sense, because basically what happened under different forum, Indo-US or Indo-Japan or Indo-French or Indo-South Africa, or we also have something like BRICS cooperation and all. There are various schemes which are developed for people across this partnership to collaborate. One of the things I'm seeing is that whenever this consortia are set up with a centralized funding, in the sense that the fund comes from one single source which are contributed by both the countries, we find that the programs are extremely smooth, because the trips are approved, your hirings are approved, because you are getting money from centralized cases. But whereas in some bilateral collaboration, you have a system that individual governments will approve, and you find that one partner will have money for that person to, and his collaborators from that country to travel to the other country. It may not happen the other way around. So I think one way of establishing nourishing astronomy collaboration is to make sure that there is whenever two countries or multiple countries are involved, the funding should come from a centralized source where each country contributes equally. So I think this can be a very important thing, which is, in my long-term experience, I found that whenever we have such a system, the project was extremely smooth, and the collaboration become like what Tarun said. You start with a simple collaboration and end up having a very large collaboration over a period of time. So that is the first point. And going to the other spectrum is related to very, very big projects like SKA or TMT or one of these big projects. Then problem is one can see that country like India will end up investing huge amount of money if you want to have a fair share of observing time in any of the facility. Then the requirement is it's from the funding agency point of view. It is important that the money which we are putting into astronomy projects also go into developing technology and technical skills in the local industries. So this is one of the conflict one faces, because if you want to be part of a consortium, the in-kind contribution has to be spent in the parent country, while the project may be happening somewhere else. So this is a very tricky situation, which means that even though we are opening up the window for collaboration across the partnership, this condition will mean that only countries which has a highly skilled people or community will be able to easily participate because they will be able to produce big instruments which are needed for this. So this is a really chicken and egg problem. If you really want to spread across big countries which are not yet technically competent enough to build big instruments, then you will find that they will struggle to contribute to this funding. So what I'm trying to say is that this requires some kind of the project management to have a kind of a broader perspective. In addition to developing the project, they have to also figure out how to develop some technical thing in every participating institute. It's a very tricky problem, but I think it will be faced when we go to the next stage. But now maybe some 4 big countries can contribute to a big project like ESOS, ELT or whatever. But if you are thinking of next generation, probably we have to go to the whatever you call not so developed and developing countries where government will ask like what our people are going to get. So this strategy will be interesting to think about. Yeah, thanks.
Yes, all very good points. Thank you for adding them. All right, I'd like to move us on to our next question. So historically, research and educators from some parts of the globe have not been as active in the international astronomy community. And I'll give you one example from gravitational wave astronomy. So I mentioned that the LIGO Scientific Collaboration has 1,400 members in 19 countries, but not one of those countries is in the continent of Africa, for example. So that's just one example to consider. But what do you see as the major barriers to more distributed active involvements? And I'd like to start with Annapurni Subramaniam. Please go ahead.
Thanks. I want to answer this question from the point of view of handling the membership, which we see applications to IAU. So we see it right across the globe, but if you see the number of members in the IAU, it's actually quite skewed. So as the chair of the committee, I've been going through these applications. So what I find is that, of course, we use a certain benchmarking when it comes to, taking who can be where, or even if you take a conference or if you take a meeting or, anything, any activity. So this benchmarking is, if you take the same benchmarking across all the countries, it's not going to work because the standards are different. The productivities are different. So if you want to have to be inclusive, like connecting to the point which Srianand is also making, because you need, when you go to the next level of collaborations, you need all countries. You need people they have to lift up and come. So you need astronomers and then, technologists and everything else. So you need to handhold them. So you can't have a benchmarking same across the board, point number one. And you cannot use the same criteria. And if you look at the applications in general, in the time one spends in teaching, outreach, research, administration, if you put all these 4 together, as a researcher, this fraction is not the same across. And it may be due to various reasons. And also, they won't have access to data facilities. I mean, the reasons being your skewed up fraction is because the access to data facilities, peer guidance and support, teams and groups, etc. And also there's no coordinated effort from that particular country as such, because there's no core organization for an astronomy in that country as such. So there are multiple factors, but it is improving over time because we are trying to be inclusive. There is data democratization. There's access to computing now. There's access to meetings online post-pandemic. So there are more number of people trying to access meetings. Physically, they were not able to come and attend the meetings, but more number of people are attending. So this has, in fact, increased, but there's a whole lot of things to do because it's very important for hand-holding required to enhance those communities who have not been able to do so. So again, connecting to Bernie's talk, it's regionally, you might see that, you need hand-holding to increase the number, but globally also this is required across countries, across continents to handhold and bring them up to the mark. And as established astronomers, you also need to be inclusive. You need to have helping them. And maybe at the IAU level itself, because some of the countries are not even member countries. And what do you do with applications who are not even members? So you get stuck with them. So there has to be processes which takes them through and make you inclusive. Over a time scale, we can really achieve it. But we need to do whatever you see in the smaller scales and take it to the larger scales to make more people come into the astronomy community and make it global and make it truly international. Thank you.
Thank you. Yes, extremely useful advice there. Let's please go next to Bernie to follow that up.
Just one point about LIGO to start. We did donate Saul Tukolsky to the whole effort. He did his BSc with me in Johannesburg in physics. And I believe he now does a lot of the calculations of black holes merging. So Africa is not entirely unrepresented. But as Annapurni says, there are lots of problems of perception and of fact that inhibit researchers from, let's say, poorer countries from participating internationally. One is a lack of resources, and that is a very real issue. So it's not so much a problem in South Africa, although it is a problem. But certainly in other African countries, there are very heavy teaching loads on people and very few resources for research. So you don't have access to laboratory equipment, you don't have access to operating funds. Very often you don't even have access to sufficient data or reliable internet connections. So it inhibits you from doing the work in the first place. There's also a perception problem because certainly if I'm faced with two papers to read and one comes from Caltech and the other one, or UBC or Toronto or whatever, and the other one comes from Botswana University of Science and Technology, I'm more likely to take the UBC paper seriously than I am the Botswana University of Science and Technology. And there may well be good reasons for that because people are working on peripheral issues where they've had access to data or they've had training in a particular calculation or whatever it is. They just don't have access to the mainstream. So in order to get people into mainstream science, you've got to have some way of supporting the institutions. And what we've done in our program is to bring people to South Africa and train them, and through the DARA program also to the UK for masters and PhD positions and postdocs. But there's a huge backlog that you have to deal with. And the way that we've approached it, because we didn't think we could solve the problem of institutional development in the whole of Africa, was to say, make sure that people have access to data that's in the public domain, make sure people have the skills to process that, make sure that they have the support to help them do the research, make sure they've got mentors, make sure they've got links. There must be some mobility funding, and it's going to take time, but you've got to be proactive. You, as I said earlier, you can't wait for people to come forward. The Royal Society has been working hard to make itself more diverse, but it's become very clear that it's not going to happen if you wait for people to come forward for two reasons. One is people in the periphery, the colonies, never even think of getting nominated for the Royal Society. It's not something within our consciousness. And the other one is that their achievements are not always ranked in the same way as they are if they were at Imperial or Cambridge or Oxford or somewhere. It's just, we don't take them that seriously. So if you try and balance the scales a bit, then you find that there are outstanding people all around the world, but there's a serious perception problem. So it's partly a perception problem, it's partly a problem of resources. But you have to be proactive, you have to go out and look for people, you have to support them, you have to ensure there are mentors You have to link them up to international research teams. You've got to involve them in real projects. And as I say, someone like Anna Scaife has got very good experience of that. I think there's some very nice examples around of how you can develop young researchers who are excellent.
Yes, agreed. And I want to follow up on a point that you both mentioned, which is the importance of data access. So I will open this up to the panel for anyone who would like to answer, or maybe one of the two panelists who just spoke. But I'm curious, what do you think it will look like when we have achieved data democratization, when we have this equitable access? Please go ahead, Gina.
I think we have to ask what we mean by that. And this gets to both Annapurni's comment as well as Bernie's comment just now. Already, there's plenty of access to the data, but I think what we are looking for is access at a deeper level where people's accomplishments are recognized for the content of what they are, as opposed to all of these other things that we often attach to that, like the institution that someone is at, or how eloquent they are, for example. And I think what it looks like is that people are able to actually achieve a scientific self-actualization, no matter what random aspect of their world line has landed them in what geographical part of the world, or in what culture. And so I think, to my mind, the democratization of data means of data access means that there is true equality of opportunity across the globe for scientific discovery.
I think that's a really nice vision. Thank you for sharing that, Gina. So let's take a question from our viewers. So Patricia Whitelock asks, would better arrangements for visas, perhaps linked to scientific collaborations for study or research, be helpful, or is this a minor issue? And I think, Annapurni, please go ahead and address this.
Yeah, this is interesting problem, and we do face from India to several countries, even though there is a wish to go, there is a means to go, there is problem with visa. So there is a wish to go is first to begin with. You need to set up a collaboration with someone, then write a research proposal or whatever it is, and then put it together. Then you need to find out the means to it, because someone has to support that, etc., etc. And having done everything, and then you are stuck with the visa thing. So there are ongoing issues, like right now, the students who have everything, Australia, the visas are very difficult. They're stuck. So these are real issues. But of course, it's like the aiding things, because when you have a larger collaboration, it's not even to do with one-to-one. These kind of things affect countries who are maybe right now I'm talking about India, but then in case if you're looking at lesser resourceful countries, the issues are much more. So more and more difficulty comes over there, and handholding them and majorly participating in meetings and conferences. The huge amount of fund is required for that, and you don't even to start with it. Getting the means for it is difficult, and then you go around doing all this. Everything is a problem. So aiding all this will definitely help to erase the number of astronomers across. Thank you.
I can add to that. I mean, that's precisely the worry that, how do you, so you may have data which comes to you, but the question is, how do you assimilate data which, says, can we make discoveries with it? But how do you do it if you're not part of the conversation? And however globalized our world is with online access, I think all of us would agree that, most of the stuff happens with people frequently visiting each other's institutions, and that is not happening across. I don't think India is as resource starved as it was a couple of decades ago, when or be very earlier. But it's mainly the question is how frequently are we, how open are we to allow scientists to collaborate, recognizing that science is, inherently collaborative, and particularly astronomy and astrophysics is inherently a global science. And that, I think, at a governmental level should be recognized. And, if there's some way of helping out on those counts. I do agree there are strategic areas which need to be maybe guarded and there are worries, but in general, I think it's fairly obvious that there are areas in which we can be very open to relaxing visa norms, or doing things which are allowing anyone and everyone to really travel across. I mean, you may in India now have the money to travel, and you may have all the access to data in many places, but what really prevents this is you're not part of the conversation, the global conversation all the time.
Thank you, Tarun. So I'd like to move us on to our final question for the panel. So how do you see G20 governments supporting the issues that we've identified for regional and international cooperation in astronomy? And I'd like to start first with Kaz, who I think has a few slides prepared for us. Please go ahead, Kaz.
Yeah, because I just narrowing down this question about what the G20 country as a government of those countries can do. And especially for, I was thinking about this data science and astroinformatics. So what I thought is important thing is the data sharing that we just discussed about, and open science. So we can actually ask, and the G20 governments can promote open science and the data sharing, and establishing data sharing policies and the protocols that address privacy and security, and also implementing that secure data management system. That sorts of things, the government level, and they need to agree on. And of course, we come back to this capacity building things. And those G20 governments can support capacity building programs. And well, in the mean of something like scholarships or grants and the training opportunities for scientists and for developing regions especially, and gain skills and the knowledge through collaborations. So these things we can actually mention in the white paper. And also, most important things, to do it, the bottom line is we need the funding. So G20 governments can allocate financial resources to support these international collaborations in astronomy, and they can establish dedicated fund or grant programs, especially for global astronomy research initiatives. And also policy and regulatory frameworks like a visa we are talking about now. The governments can create supportive policies and regulatory frameworks and facilitate international collaboration in astronomy and develop clear agreements on data sharing. This is very important. And the intellectual property rights and publication policies, so on. So this we can share the data, and that we can promote astroinformatics. And also we ask governments to invest on the public outreach program, and also the technology and the infrastructure sharing, what sorts of protocol they can actually come up to sharing technology and the infrastructure. So these are the things I came up. And of course, you have some comments and also some ideas. Please, if you don't have enough time, you can actually send an email later, but that's I got.
Thank you, Kaz. That's a great summary. So we do have time for one or two more comments, and I'll open it up to the rest of the panel. If anyone would like to offer one last comment. Please go ahead, Tarun.
Right. Following up, I mean, one thing that occurs to me, although we do see, I mean, we've grown up in a time when India was seen as a developing country. I don't think that's true as much resource-wise. So, I think it's also time for regional regionally taking people along. I mean, there should be some champions countries coming along and taking a region. I mean, I can see that, if I'm not wrong, South Africa is playing that role for the African continent. And similarly, I mean, since this is G20 hosted in India, I think it's really the time when India also reaches out and tries to be more regional than the country. I mean, and we have enough capacity to do that, but and we have uh, enough points to connect to what would be called the leading countries. So we'll not be leading in some things, but there are, like, we have fairly large communities in frontier areas, and the one way to grow is not necessarily to always see how to partner with leaders, but how to create a follower group. And we have an immense challenge doing it within India itself, as Anand pointed out. I mean, we have universities which are underprivileged and this thing, but that should grow into a slightly bigger role, and we should open out more. And that's one point I wanted to make.
Thank you, Tarun. I think that's actually really excellent points for us to leave on with 4 minutes left on our break before the start of the next session. But before we close the panel, are there any other parting thoughts that any panelists want to share? Please go ahead.
No, I just see. I didn't know exactly which level we are talking about collaboration. For example, whatever we are discussing is at a very high scientific level. But G20 is very interesting because if you look at G20 countries, they host all the biggest facilities, astronomy facilities, and some of the members of G20 don't even have basic level astronomy. So what will be interesting if you are thinking in terms of spreading astronomy, one of the things we are trying to do in India is to make sure that some basic intellectual level material, which is developed in English, be translated to all the local languages so that the young kids can read in their language. So if one is looking at G20 at the education level, effort can be made to collate advanced level materials which are developed in a country which is advanced in astrophysics. If it can be translated to local languages, either in Africa or in Asia, I think we are going to do it in India ourselves, but it will be good to do it across the thing so that we are not only worried about establishing big facilities, we are also going to create curious minds starting from schools. So this will be one thing one can propose probably.
Thank you. An excellent idea. All right. Thank you again for all the panelists for the great discussion. Really appreciate your time, and we've got a lot of good ideas here. We'll follow up with those soon, I hope. Thank you again,
Thanks, Jess.
everybody.
Thank you.
Thank you so much. It was a great panel. We take a short break and then we come back very soon with the Dan's talk, which will be followed by the panel on space data requirements and astroinformatics. We'll see you in about 10 odd minutes. 15 minutes, actually.
We could make it short, right? Because I think there are some other people who need to go later. So 10 minutes from now, maybe?
10 minutes from now looks good.
Check.
Be starting in about 5 minutes.
Ashish, can you check that the microphone works?
Pepe, your microphone works.
welcome back to the last leg of this exciting Science 20 policy webinar, Astroinformatics for Sustainable Development. In this last part, we have one talk by Dan Crichton from JPL. So Dan, if you want to share your slide and just test that, and then we'll have another minute and a half before you can start.
Good, okay, let me see. How does that look?
That looks great. This is being live streamed on YouTube, where a few people are joining, and it'll be looked at later on by policymakers and others. And the main product is going to be a set of white papers on which people have been working. And then at the end of the session, so after this talk, we have 2 1-hour-long panels, and then we'll summarize the meeting and talk about the process for the white papers themselves. So the talk Dan will be giving will be on space data requirements, architecting a data-driven future. Dan is the program manager and principal investigator at JPL, and he's been leading various things related to planetary data science as well as methodology transfer to medical data. So we have a large data set from various cancer institutes at JPL. So how the transfer of knowledge happens from one field to the other. Here he'll be talking more about the space data requirements, and that's the panel we'll also have following this. So Dan, please take it over.
Thank you, Ashish, and just congratulations to you and the other organizers for just putting together a really well thought out program. And, you know, I just applaud the thinking about recognizing the importance of data and how that is really transforming the opportunities for us to be able to extract and get more yield out of for science. And I think we're living in an exciting time where we've got so much data, so much computational power. We're now looking at how do we harness that, and how do we begin to really look at ways in which we can take the full life cycle to look at the capture of data all the way to how we analyze it, and look at ways in which we can really increase the output we can get from working with our data. A little bit about JPL. I'm sure that my colleagues around the globe know about JPL, but you know, we and Ashish mentioned this, we think about methodology transfer because we're thinking about the sensors and ways in which we collect data here on Earth, as we look at our planets, and as we really turn our sensors and cameras to explore the universe. So looking at ways in which we can bring all that data back. And some of the challenges that we tend to have is that we've got to be able to really bring data back across the solar system. And so we're really building an intergalactic network, if you will, of sensors, really being able to extend our computing infrastructure, not only here on the ground, but into space. So as we think about the data, where we compute, how we reduce data, how we transfer that data, ways in which we can make decisions about our data matter. And so really what I tend to think is that we've got some of the most interesting use cases, but data and computing challenges that exist, because we're really trying to operate a data system across the solar system. Part of the challenge is that we need to bring all that data back through our deep space network. So our deep space network has a communications infrastructure that always has line of sight to the spacecraft as the Earth is orbiting. And so we've got 3 points on the Earth where we've got the ability to receive and transmit data in California, in Spain, and then also in Australia. And part of the challenge is being able to really bring enough of that data back that we can begin to capture and work that data. What we've seen around Mars is that we have such high definition cameras now that we can only return about 1% of the data. That means we have to be very, very selective about how to prioritize what data we return, and what computation we do on the ground versus what computation we are doing on board. So as we really begin to think about our data requirements, it's looking at how do we begin to capture the right set of data. How do we begin to make that data available to the scientists? What can we do to begin to prepare that data on board? And how do we begin to enable more and more autonomous capabilities on board that can begin to process data as close to the sensor as possible, and then bring back the data that's really critical for long-term preservation, use, and continuing to support exploration in science. Part of what's been shifting, and this is really different from when I started working with the planetary data system in about 2001. 2001, we had captured for the first about close to 35 years of exploration, about 4 terabytes of data. Today, the planetary data system has about 4 petabytes of data. So you realize in 20 years, we've captured, I'm going to say astronomical, we captured a massive amount of data that we hadn't captured previously. And that's really shifting the way in which we need to work with our data. We've gone from this data poverty, where we don't have enough data, to a data glut. And we're seeing this in astronomy. We're seeing this in our Earth orbiters, where we've got so much data. We've got to look at ways in which we can begin to filter, extract, find that critical data information and features that are important. We're moving from data sets to more data streams, data that's always constantly flowing. If you know the NSF's whole big data 5Vs, it's really looking at velocity and variety and all the challenges that are associated with the amount of data that's being generated. And so being able to change ways in which we can capture and operate on these data streams and begin to make that part of how we're responding to the data. So it's not only doing science after you capture the data, but pushing that science and that mission operations all the way up to the platform. It's moving from static to dynamic and evolving data that's continuing to improve. And that whole data stream concept is really moving us more and more towards this need to think about more and more real-time analysis and discovery, which will enable more event detection and response, and our ability to integrate our instruments and our sensors with the way in which we want to do science, to be able to command those, to begin to do the kinds of science observations that are needed to continue to expand our knowledge base. Moving from what we used to have with centralized data resources, we capture data in single archives and so forth. Now those are distributed. They're worldwide, and I'll talk about that. So all of our science disciplines, whether it's astronomy, whether it's planetary, whether it's earth science, all are forming partnerships for us to begin to provide and support worldwide science. So we've got to provide ways in which we steward, fund, provide open, transparent access, be able to link to the data, be able to cite that data, be able to support the reproducibility of that data in terms of being able to ensure that we've got really access to that. And that requires understanding how to work with the data. So being able to have the expertise of those that understand the data. And so it used to be where we're going to capture this data and we'll put it here. Now we really are thinking more and more about how do we begin to identify those discipline experts that really understand how to work with the data. And we see that in the planetary data system because we tend to organize the planetary data system around expertise more than just ownership of the data. What's happening then is with all this data and computational powers, we're seeing an explosion. So what was big data, say 10 years ago, was the concern of how to begin to capture this data, how to begin to process the data as it's increasing and support the analysis of that. And so the big data challenges began to occur as the data began to exceed the computational capacity of the systems that we're trying to manage and support its analysis. That launched data science to say, how do we begin to then apply methodology, architectures, algorithms, begin to extract and provide that insight in terms of the data collections that are being captured. And more now we're moving into the era of AI, where we really want to provide more and more reasoning and understanding of that data. And we're moving that direction to say, how do we begin to provide ways in which we can start to mine, extract, represent, reason, and provide more computational and automated and autonomous responses to the data that we're capturing. I like on the right, I show the Carnegie Mellon University AI stack, because I think it's really important to think that this is not one piece, but it's really an integrated architecture that thinks about the computing infrastructure and the devices that observe it and the massive data management that's capturing it, and then the algorithms that are working with it and the models that are implemented with those algorithms and the ways in which we make decisions from those models, and then we act and drive that autonomy. And so ways in which we begin to realize that we cannot think about data independent of our computation anymore, independent of our observations and sensors. We got to think about how that all comes together and where the trades are made. I also like this view, which is saying, you know, as we hear these definitions, what do we mean by data science? What do you mean by artificial intelligence? What I've told several of the groups I've talked to is the fact that trying to parse these terms is probably not helpful. Looking at how they come together is important to realize that data science and AI need to work together and have foundations in mathematics. They have software systems. They have computation, high performance computing. They have sensors that are taking their measurements, and there's a whole number of capabilities that need to be supported to be able to really enable social science, natural science, health science. And we're seeing this kind of pattern occur in many, many different areas. Ashish mentioned that one of the efforts we've been underway is I've been a principal investigator for the National Cancer Institute for the last 20 years, looking at how do we take what we do in planetary science and astronomy, where we're taking observations and data and begin to support then the discovery of cancer biomarkers by looking at imaging data or time series data or analysis or other kinds of information, and start to create those models where we can begin to then find enough statistical power to identify markers that might be indicators of disease. So these kinds of ways in which we want to do data analysis from our data and move to more and more of this data science or data capability is really really cross-cutting in many of the sciences that we're now seeing today. And that's really shifting then the way in which we think about how we do science. The traditional approach was, you know, we create a hypothesis, we do our experiments, we collect our data, we perform the data analysis, and then we publish and produce our results. But more and more, we've got the ability with so much data to actually help do these in parallel, to begin to refine our hypothesis, to begin to do some data exploration early on, begin to use that to then help support and improve the kinds of data collections we're doing and the analysis that we're going to do with that data. And so looking at how data-driven methods and traditional hypothesis-driven science approaches can come together is really, in my mind, the future of where we need to head. And that really supports then the way in which we look at a modern scientific discovery process, which is we're doing data gathering. So we've got instruments and sensors, we've got pipelines moving data and computing, and we're capturing that data into these massive data farms. So we're archiving that, we're labeling it with metadata, we're providing the ability to be able to index and search and find that data. And then we're looking at ways in which we can begin to combine that data for greater insight. We're now in this era of more and more data-driven analysis. So data mining capabilities, machine learning, being able to do image analysis, classification, feature extraction, looking for those kinds of pattern matches that exist both with supervised and unsupervised learning, and ways in which we can then take the results of mining all that and drive new understanding. And so this is the paradigm that we see occurring in many, many, many different areas. And what is happening in space and earth science and planetary science is the fact that this whole approach is being spread across all the way from how we collect data all the way to how we analyze data. And that's a massive data life cycle. And so you see that here in this picture. One of the things that's been shifting with earth science is we're in the hundreds of petabyte scale data now. So we moved from say a mission like SMAP, which is a soil moisture, looking at soil moisture in the measurements, to NISAR, which is going to look at surface deformation changes, things like earthquakes and so forth. And you can see the massive increase in the amount of data that's being generated per day. So NISAR is going to generate about 80 petabytes. We're seeing these same kind of challenges in planetary and astronomy, where we've got massive amounts of data. And so we cannot transmit, particularly for planetary science, that data through the deep space network, through our communications infrastructure. It's just too much data, and we don't have the bandwidth capabilities. We also have limited onboard computation. So we've got to make decisions about what to compute, what data to transfer, what the prioritization of that is, and then how we begin to then capture and intelligently use that data and make that available for science. So in many ways, where we're moving with big data and data science is building is really operating at the extreme edge, looking at how we push computation all the way to where the data is being collected, and then making important decisions about how data is being moved throughout the system so that we can get the most yield out of our data. So as we look at this at JPL, we're seeing all of these areas as really disrupting the need for us to think about new areas for how we work with our data. So autonomous systems, which need our data, AI, machine learning, which it needs our data, both on board and on the ground, and to enable science. So we're seeing it in many different areas. Data science in terms of how we're capturing that data, how it's all distributed. And so the future is really how do we begin to provide those capabilities and then have the right computational support to be able to work with that data on board or on the ground. And so this is really one of the shifts that we believe is going to happen with working with our data is moving more and more autonomy and AI and data science on board to support things like real-time adaptations, to be able to support more high-end high-performance computing on the spacecraft, be able to support more of the data processing we need there, and really to begin to make more event detection and feature detection right at the point of collection, so that we don't need to transfer all that data, but we transmit what is important to transmit in terms of being able to capture the science record and to be able to reproduce and understand the results. And so one of the challenges is that, as we look at this massive amounts of data and we look at what's happening with data science, we go to something like Google or Amazon and we see this, and I'll talk about this with things like large language models, so forth. We train those on hundreds or more of GPUs. So these are massive, like trained models. And we just don't have that capability on board. If you look at things like the Voyager spacecraft, it's 8,000 instructions per second. You've got your iPhone, it's 2 teraflops and gigabytes of memory. If we go to things like the fastest supercomputer, at least when I created the slide at the Oak Ridge National Labs, you see the computational power there. So we've got the computational power, and the question is how do we begin to now take advantage of all that data being generated? So bringing that together in terms of how we observe and do space science research is going to be really critical in the future. Sorry about that. One of the most interesting things we've done with our data, in my opinion, is when we landed on Mars for Mars Perseverance, we used a landing vision system, which allowed us to begin to then basically identify almost like a GPS capability to identify and pinpoint the exact location where we wanted to land. So this was our terrain relative navigation. And we really touched down about 5 meters from where we had intended in a very, very hazardous area. So really, really incredible to see the fact that now we can take enough data, we begin to build models, we can begin to take that from our archives that we've captured now and be able to inform future landing systems. That's just one example. If you think about all the data we're capturing, so that the important thing here is that we've been capturing the data that we can now use in terms of driving not only new science, but new mission operations capabilities. Here's another one that I like as well, which is looking at how do we push capability on board. So this is looking, as you see moving across the surface of Mars, dust devils. And so we always knew that those existed. If the camera was pointed in the right way, we would take an observation of those. But then we began to put software on board with trained models that begin to identify these features and begin to track and turn on the cameras so that they could track and capture those dust devils. So what we're doing is we're not moving that data down the ground to process, because they would be gone. We're pushing that computation on board so we can instantaneously do the event response and capture the data. And really, that's really been a game changer now for helping then bring in new computational capabilities to work with our data directly on our rovers. And so you see the example here where we're actually tracking those various dust devils. Moving towards the ground, then there's really an opportunity for us to look at how we can automate and work with our ground system capabilities. So looking at ways in which we can use and look at communications channels to find anomalies, looking at ways in which we can better support mission operations looking at ways in which we can start to capture and build archives where we can begin to support data-driven discovery from our archives. So you have labeled data and ways in which we can then bring in and support interactive visualization. And so the capabilities of AI, machine learning, and deep learning, and building better search and so forth are really opening up now the opportunities to better work with our data. And we're seeing more and more ways in which emerging capabilities are exploiting our data. So that we're at that point where having captured all this data now is really important. If it's well curated, well captured, and well defined, we can feed it into then these kinds of tools. This just shows the growth pattern that I mentioned. You would think that we started planetary science observation back in 2001. That's really not the case. As I mentioned, we had about 4 terabytes in our archives, but you've just seen the massive scale increase that we've captured. And as I said, we're really pushing closer to about 4 terabytes now. As I mentioned, you know, the one of the things I think that NASA's done well, but also the international community is working together to begin to build these massive archives. So we're at the point of now building petascale data archives, massive repositories based on standards. So, you know, whether it's FITS or PDS4 or HDF, providing ways in which we're standardizing the structure of our data and looking at how to bring that together. We're now at the case of how do we take that data, make it AI ready or analytics ready, analysis ready, to begin to then feed the machine learning and AI capabilities we need next. And so there's a lot of effort to say, how do we go from data that's been stewarded to then supporting the analysis of that data? And so we've got a data science program at JPL, which has really identified that as the gap of, as we begin to do the analysis, we've got to take and start to wrangle our data into structures and ways in which it's labeled and can be supported to do analysis, so we can create the appropriate training sets and start to build machine learning models. One of the other pushes that's happening in NASA has been a push towards open science. And so it's looking at how do we provide transparent access for the worldwide community to not only our data sets, but the software algorithms that produced it, to the publications where they're defined, and support really the reproducibility of those results in those published works. And so we've got a requirement now at NASA to begin to make sure that that's open and accessible. And I think the work that we've done in the archive community really provides us a foundation for how we can provide access to that data. And we've been working with publishers and others to begin to capture that, to link publications to the data and provide access to the publications. But we're now at a place where all of our software is moving more and more towards open source as well, so that the results can be reproduced from the publications using the data and employing the software. Part of what we've had to expand was as we've captured our data in these massive archives and we've looked at the whole data end to end, is making sure that our data is labeled not only for data management and stewardship and discovery in our search engines, but for analysis and use in AI machine learning. And so we've been starting to work with more and more tools. I know the Zooniverse was on, I was really happy to hear that, to be able to start labeling the features and things like that, because we're seeing that need where we start to find things which are not defined in our metadata. We want to be able to provide more and more insight with labeling our data so that we can then inform our models. And so the foundations we've laid, and we've seen this in planetary science, are now launching dictionaries for machine learning, which we haven't had before. So now we can have a dictionary on imaging, be able to have imaging features, things like that, which are important, and then publish those standards so then we can exchange models and we can exchange data sets that can then be used with those models, and new models can be developed as well. So this whole push towards capturing open, transparent data and providing ways in which we can access that has really been critical for driving open science. And the Planetary Data System launched the International Planetary Data Alliance back in 2006. I was part of that. And in 2012, we agreed on standard models and ways in which we can define core metadata for planetary data. The work of IBOA has been excellent having that in place and having these international bodies that can work together to define data standards, provide open, transparent access, and exchange data is critical. And what I see going forward is those communities are going to start to share training sets and models and be more and more AI ready. Just an example of how we've now applied things like machine learning AI. Here's an example where we're doing crater detection on Mars. We're taking that labeled data, being able to build a database of images where we can begin to search and then train our models, begin to find certain kinds of features and landmarks in some of our imaging data for Mars. We've seen that same thing in astronomy. And in fact, one of the things that we did I'll give credit to Ashish Mahabal, was that we were able to take work that we did in transient detection with images and then transfer that over to cancer research and show that the same kinds of capabilities can be applied in methodology transfer between various science disciplines. And of course, we've seen the same kind of thing occurring in areas of earth science. So here's an example on the left of finding methane leaks and detection, which used to take us about 3 months. We're able to do it in 48 hours, work with airborne missions, be able to capture that data and respond in more real time. Similarly, we've been able to take data sets and start to improve the way in which we look at what's known as rapid intensity to identify whether a hurricane is going to form, be able to provide improved prediction of what's happening with hurricanes and other data. So we're seeing more and more opportunities as our data is being captured, as computational methods are being put in place, as machine learning capabilities are being improved to be able to apply these kinds of methodologies to then provide greater insight. And I'm going to start to wrap up. So one of the things that's been emerging is in machine learning is something called foundational models. These foundational models we're now seeing in things like large language models, where we can train those in large textual data. You can use that. You can then extend those with additional textual data. But we're now seeing the case where we may have models that we can take and reuse across disciplines. And so we've seen that with, as mentioned, with large language models. We're also seeing that now with imaging models. And so Meta, Facebook, for example, has published something called SAM, which provides a foundational model for image segmentation and so forth that we're looking at. So we're exploring how do we use these kinds of models with our data, and can we begin to provide improved accuracy and improved performance of these models if they're trained on massive billions of objects themselves. And then finally, one of the things that we've done to look at this whole question of how we move more computation into space, and Rich Doyle, who's one of our panelists, is part of this, was to support or look at what it means to push cloud computing into space, and thinking about the fact that we can't move all that data to the ground. So can we provide more computational and data assets around Mars, for example, and provide those capabilities to compute there. But that would require having more and more computational capabilities that can scale as close as we can to the point of collection. And so there was a study done at Caltech with several groups that looked at what would that look like, say, 10 years from now, if we begin to think about more and more of these capabilities, not just being on the ground, but being in space, so that we can begin to train models, run those models, work with our data right there as close as we can to where that data is being observed. So with that, I'll wrap up and happy to take questions and move on to the panel.
Thank you very much, Dan. Are there any questions from those who are present? You can raise your hand and unmute yourself. Meanwhile, let me ask one question. So where do you see us going 10 years from now or 20 years from now?
We are in the place where we cannot sustain moving all that data down to the ground. And so I see, as I mentioned, our need to really think more and more intergalactically end to end and pushing more and more of the data analysis on board. And I think that's going to be key. I also think we're going to see more and more opportunities for methodology transfer between disciplines. And so it's going to be important for us to work not only within our discipline, but across disciplines to figure out how we can share and leverage each other's capabilities, because I think that we're seeing that opportunity and the power of being able to transfer models between various science disciplines.
Right, and I think one of the biggest challenges is going to be that on ground we have many data sets with terrestrial data for training, whereas when we encounter new things, we may not have that. And So do you have any thoughts on that, how we could handle that?
Yeah, we have we still have a lot of challenges in terms of data wrangling. And so what we find when we fund a project is that something like 70% of that project goes to just say the first analytics. So being able to get the data prepared, make it search labeled, so forth. And I think part of the challenge is making sure that our archives and the data that we're collecting are labeled and ready to help us reduce that analysis and really drive more capabilities as in a more rapid fashion than we are today. And so looking at ways in which we can provide that kind of labeling, I think is going to be really, really critical.
Great, thanks. Any question from someone else online?
I just had a question. In order to improve the analysis capabilities on board, is there any plan like TDRSS for downloading data? Are there going to be any plan for separate satellites which could analyze the data on those satellites and then downlink them? So is that there, Dan?
Yeah, there is that, and looking at ways in which we can push as much of that computation on board, and then also look at, we're seeing this more with sensor webs, but being able to also direct sensors together to be able to make observations. And so this is where we get more and more into this autonomous capability to say, okay, let's set a science goal or a capability, and then have those observations take place by having those sensors commanded to be able to obtain that science and process that, and then return, highly processed science data. And so that's that's a vision that's there. There's pieces of it that we've demonstrated, but I think there's technology work going on at NASA to look at that future.
Great, thank you, Dan.
Thanks.
And I think that's a good point to segue to the panel. I invite the panelists, and Brad Senko will be leading it. So Brad, take it over, introduce yourself and the other panelists, and get good.
Really excited about the opportunity to chat with such a distinguished panel today. My name is Brad Senko. I'm at NASA's Goddard Space Flight Center here in Greenbelt, Maryland, in the United States. I am the PI of the Neil Gehrels Swift Observatory, which is one of NASA's currently operating astrophysics satellites, and I study gamma ray bursts and cosmic explosions of different kinds. So I thought we could start out. Everyone on the panel could introduce themselves briefly. Why don't we have Laurent? You want to go first?
Yes, so my name is Laurent Heyer. I'm from the University of Geneva in Switzerland. I've been working on the Gaia mission since 1988, so far, so nearly a quarter of a century. I lead the task of the processing and analysis of the variable source, which is leading to the different data release of Gaia.
Excellent. Thank you very much. Richard, you want to go next?
Thanks, Brad. I'm Richard Doyle. I'm semi-retired from Jet Propulsion Laboratory. I'm still active as a consultant in various contexts. The role that I retired from was Information Data Science Program Manager, and I worked very closely with Dan Crichton in that context to start moving along with the challenges of data science, AI, and autonomy, and all that Dan described very capably. Looking back over my, if you can believe it, a 40-year arc career, I always felt privileged to be working in this confluence between computer science and space exploration. And I think we'll be discussing more of the interesting topics that come up during the panel. Thanks.
Thank you very much, Richard. Sita? Sita, I think you may be muted. At least I cannot hear you if you're speaking.
I'm Sita. At present, I'm working at the Raman Research Institute in Bangalore, but I have retired from this the Indian Space Research Organization. And as the former director of the Space Science Program Office and as the PI of AstroSat, I was responsible for making sure that the space science data is available for the scientific community at large. And I think that's one of the reasons I'm here on this panel. Thank you.
Yeah, thank you for being here. And last but not least, for those of you who did not see his excellent talk just before this, Dan Crichton, why don't you introduce yourself in case people are just joining now?
Sure, thanks, Brad. So I'm Dan Crichton, and so I lead JPL's data science program, which really cuts across our science areas and engineering and technology programs. And prior to that, I led the planetary data systems engineering and software activities. So I led the development and definition of the PDS for architecture and data standard and implementation of that, and helped to start and launch the Interplanetary Data Alliance as an international collaboration. So thank you.
All right. Well, I have some questions written down here. I hope this turns into more of a discussion.
Brad, sorry, did we hear from Giuseppe?
We did not. Giuseppe, are you on our panel? I didn't think he was, but he's more than welcome to join us.
Oh, okay, my mistake. No problem.
I am not to your panel.
Okay.
I'm just listen.
Well, please feel free. We're happy to hear your thoughts if you want to chime in at any point. So I wanted to start out just quickly thinking, most about the science that we want. I think a lot of us are excited about, astroinformatics and what it can do in space, mostly because of the science that it's going to yield to. So I wanted to go through and just ask everyone first, what do you think is the most exciting scientific opportunity that's directly enabled by astroinformatics in the next 10 years? And I can start with this. Personally, I'm most excited about the opportunity of combining observations that we do in space of the electromagnetic spectrum, combining observations with light with observations of other cosmic messengers. And there's a large space project called the LISA, the Laser Interferometric Space Facility. It's going to actually search for ripples in space-time, gravitational waves from objects like supermassive black holes out in the distant universe that are merging. The data challenge associated with analyzing these measurements is quite significant. You're seeing the gravitational waves from all of these sources at a given time, and so you have to tease out different signals from all the different sources that are there. These are spacecraft that are, separated by a million miles up in orbit around the Earth. So it's a very technically challenging problem as well. But I think the things that we can learn about supermassive black holes, about the evolution of the universe, are just really fascinating. And that is slated to come online, hopefully, about a decade from now. So why don't we go around in reverse order? Dan, if you want to go first, and just, what science are you most excited about?
For me, it's really looking at ways in which we can start to find new kinds of observations and insights in the data that we haven't seen before. So, the fact where we can use machine learning to find anomalies, maybe those anomalies are really a new kind of science phenomena that we haven't even discovered yet. We need to start to classify and understand. And so I'm really excited to see, can we begin to apply these kinds of data-driven approaches onto new kinds of observations and couple that with our old data and see whether or not there's new kinds of science discovery and insight we can actually gain from the data. So.
Yeah, that's great. I think astronomy often is such a discovery-driven science.
Well, what I love about astronomy too is that we're observing a fixed a structure in the celestial sphere, right? So it's all defined, and we can go back and we can reclassify. We can find new data. We should look at ways in which we can go back and re-examine and remine our data to see whether or not there's new discoveries going to be made. And I think we're going to have the computational power to do that.
Excellent. Thank you. Sita, would you like to go next?
Yeah,
Sita,
so
are you there? Yeah, go ahead, please.
yeah, the data in astronomy is really increasing exponentially, as Dan showed. And considering its data in astronomy, we also want to store an archive decades, if not centuries of data, because that is essential for comparing the data. Not only that, but also comparing how the celestial objects behaved a few decades back and now how are they changing and so on. So that being the case, some way of using artificial intelligence and machine learning in order to not lose information and at the same time reduce the storage. So that I think would be the most challenging thing in the coming years. And we've seen that recently the pulsar timing array has used 15 years of data to come to the latest results on the gravitational wave. So we will need to store and archive a lot of these data sets. So yeah, Dan has proposed several things, and onboard data analysis is going to be really resource constrained. And that's the reason I asked, just like we had TDRSS to actually download the data from the main satellite to the TDRSS satellite to download slowly to the ground stations. Are there going to be intermediate satellites which can be used for processing in space before downloading to ground, but they're not done in the actual science missions themselves, which might be much more resource constrained. The second point was I wanted to know if there are people are shifting from data download to actually science platforms where people can do analysis and download only the final results. Gaia is an excellent example for that. So are there ways where, again, we can use intelligence so that repetitive processing is not done? Somewhere, if there are many users asking repetitive things, is there a way to store that and jump steps so that you save resources?
Okay, thank you very much. Let's give Richard and Laurent a quick opportunity to chime in on science, and then we can go into some of the technical questions that you raised there. Richard, do you want to go first? Science you're excited about?
Thanks, Brad. So I'm not a professional astronomer, but I will do my best to answer your question for science rather than data science. I've felt privileged over my JPL career to often be on the front line hearing about the amazing developments in astronomy in the last few decades. And that includes, the mystery surrounding topics like dark matter and dark energy. So I certainly look forward to seeing what role data science, perhaps AI, can play as we continue to characterize and then gain insights as to what's really going on there. For example, if there are dark matter interactions that aren't just gravitational, and what is dark energy really? It's such a mysterious aspect of the universe, and how those insights may drive future large-scale simulations and cosmology about the future of the universe. On a more personal level, I'm probably one of many who holds out a faint hope that maybe in my lifetime we might actually see Betelgeuse go supernova, and that won't be a problem for detection, certainly. In fact, I think it could quite possibly be a daylight object, but But if that were to happen, there's going to be all kinds of data and interesting analysis that we'll be able to do on such a phenomenon. Okay, thanks.
Those are two great responses. Thank you, Richard. Laurent.
Yes, as we heard, the data growth is enormous in terms of volume, but also in terms of variety. You spoke about multi-messenger, combining gravitational waves and optical, but also my point is that within the optical, there is a merging of data, like how to merge astrometric time series, photometric time series, and spectroscopic time series. That's typical problem we have in, or challenge. It's a problem, but also it allows more to do more. So how to deal with that? And to have an enormous amount of time series of spectra, either the BPRP of Gaia or the RVS instrument, is a fantastic opportunity. And I think there we don't have totally the tools. So what can we do, for example, is combining astrometric time series, detailed astrometric time series of Gaia with a photometry to detect single black holes. Because how do you detect single black holes? You detect it through microlensing. And there, by combining things, you are able to lift the degeneracies you have in the field. The other point is how to combine photometric time series of different spacecrafts, for example, of TESS, Kepler, and Gaia. And there, the characteristics and the reductions are very different, and it's very tricky. And when you want to learn the physical origin of the variability, you need to combine all these information. And as a third thing that I was thinking there is, I mentioned it, is how to use these time series of spectra. How do you look, for example, in a periodic change in your spectra? So there are ideas there to where you need high computing power, new method to explore these domains.
All right, excellent, thank you. Let's dig into some of the technical details that you all brought up. I want to start out talking about communications, because that's something that came up in Dan's talk and something that Sita mentioned. So we have this, on the one hand, we have, ever growing larger data sets that we need to get to the ground, and we want to do it quite promptly. On the other hand, there are, new commercial capabilities that are being developed to provide, communications in low Earth orbit. NASA is working hard on the Lunar Gateway with the expectation that there will be, astronauts returning to the moon in the near future. What are the prospects, and how does that depend on, where exactly you are in space for getting the data down to the ground in as much of it as we need in a timely manner? I think that's maybe a question for Richard and Dan to start. We can go from there.
Dan, shall I start?
Go ahead, please.
Okay, yeah. So I'm going to open up that question a bit. It's because communication touches autonomy and computing on board as well. So looking at that whole picture, I think we're starting to see really across the several disciplines, earth science, planetary, and astronomy, the use of what we might call event detection and response architectures, where you want to have a certain vigilance to detect interesting phenomenon, but then having detected it, to be able to quickly pivot perhaps to a different facility or a different spacecraft or a different instrument to do follow-up observations. And this becomes more challenging if it's a transient phenomenon. I mean, we're all familiar with this. In the earth science arena, it's often about hazards such as forest fires, volcanic eruptions, floods. In planetary, Dan talked about dust devils on Mars as a great example of a transient and dynamic phenomenon that we'd like to be able to study. And then, of course, in astronomy, there's supernovae. So the key is looking at that architecturally so that you have the flexibility to mount a response to a detection, but not necessarily from the original sensor, instrument, or platform that performed the original detection. Sometimes this is called sensor web concepts. And again, we see that across all the disciplines. So timeliness is always a driver. And as far as communications, we're seeing advances in optical communication, so that holds a great prospect for being able to move more data. But Sita also teed up the topic of what can we appropriately do on board and how do we enable that. So Dan mentioned some advances that are underway with flight computing concepts. I'd like to point out that communication and computing are not necessarily opposed or like in some kind of a trade relationship. We should think of them as kind of a rising tide situation. Even while we pursue optical comm, we should also be pursuing more capable flight computing and thereby create all kinds of new possibilities for able to do analytics wherever it may be appropriate. I'll just make one more comment, and this is about, we're all familiar with the term edge computing. JPL does a lot of work in the planetary arena, and often there's sort of an initial blush assessment that edge computing is not really going to be available at the edge of the solar system because of the communication difficulties, or to put it differently, you can't really burst into the cloud easily from the edge of the solar system. However, if you look at that more subtly, again, from like a data flow or architecture concept, imagine detecting some interesting phenomenon in a remote part of the solar system, say one of Saturn's moons. You can imagine analytics on board that do the detection and perhaps do some initial processing of the raw data to create intermediate artifacts and results. And with the idea that there are ground-based cloud resources available, but instead of sending the raw data or some slice of it, you send intermediate products that will then kickstart a much deeper analysis once those more compact products get to the ground and can access the large clouds. So it's kind of a two-step process. Again, it's kind of architectural thinking. So you can take advantage of the cloud from deep space, but perhaps in a two-step and other subtle ways that we need to be thinking about. Okay, I'll turn over to Dan.
Yeah, I think Richie, I think you did a great job answering that. I think that the one subtle point I was going to make is, and this goes a little bit back to Brad's comment too, is what we found is that there's not a one size fits all that works for earth science or planetary science or astronomy, because you have to look at a bunch of the dimensions related to where is that satellite, where is that spacecraft orbiting, how far is it from Earth, what's the line of sight, all those kinds of questions. And so Earth orbiters tend to have a different answer in terms of how it may work on board with the ground versus what we do in planetary and so forth. And so what we found is some of the data requirements for Earth around this may differ from those in planetary science.
Okay, excellent. Let me dig in a little to something that Laurent was mentioning in his kind of opening remarks. You gave this really nice example of, finding isolated black holes, combining time series data from Gaia with spectroscopic measurements from the ground. I think you're totally right. This is, combining these heterogeneous data sets is enabling really new and powerful science, and something that we're going to see a lot more of. But it also introduces lots of technical and computational challenges, right? Because, time series data, I think kind of a sense of how to handle that for the most part, but now you're folding in a very different kind of data set. What do you think the big roadblocks are in combining these heterogeneous and diverse data sets? And, how do we make progress in really sort of enabling new science by making those connections?
First, maybe a comment with difficulty, because the science in a way is defined by itself when done by scientists, I would say. And so we see that scientists are very independent characters. And so people, often many scientists like to develop their own tools and their own methods and also their own format. And so that's it is a bit a difficulty. On the other side, you have many initiatives to uniformize things like virtual observatory, but also within Gaia, we have a binary Gaia format to transfer data. And then we see that sometimes we had difficulties also with software engineers which are developing tools, typically a visualization tool to look at the Gaia data time series, and that didn't pick up until there is one person who developed a tool that was spread among more people in the consortium. So it's a kind of work hand in hands, the technical people, software people, and the scientists that should go together. And there are many problems there. So, for example, I was always surprised that if you visualize a few time series, it is easy. If you have hundreds of time series, it is easy to summarize and to look. But when you have a million, or I don't know, half a billion, then it's a problem. Or even scatter plot. When you have scatter plot, you have few points, but there is suddenly you reach a level where you need to do tricks to visualize the data. You need to have to develop really kind of special tools dedicated to the experiment or the scientific problem you want to do. Another problem is that in these things is that you have, in a way, the raw data. In the case of Gaia, I speak about the experience of Gaia because I know it. So there were a significant processing on board because you can't transfer, I don't know, 1 billion pixels every 4 seconds. So you need to have a strong reduction of the data to transfer. And then you have a successive processing, which is done by the Gaia consortium. And then that's questioning the problem of provenance. So you have the catalog, and you want, in a way, to know what are the different steps from the data that are received or that are taken by the spacecraft, sent to ground, then the different step of processing. And I see that it is, in a way, important. So we have ways within the time series analysis to tackle with this provenance. And so, as I mentioned, there is this question of provenance. There is a question of unique, in a way, a format to transfer data. There, this question of transferring data we see in the Gaia archive. You have different formats you can choose in CSV tables, in VO format, etc. You have a series of these formats you can transfer. And also this question of merging data from different spacecraft or ground-based data, then the comparison is often tricky because of the different photometric bands. And if you want to be precise or accurate there, you need absolute calibration. And then it's coming a bit of, you need to go into the nitty-gritty details of every survey, in a way, and it's very tough. So there I have no solution for this last point. You need to go into the details.
Okay, great. Thank you, Laurent. Laurent was talking about bringing together scientists and software developers and people from different communities. We expand that out a little bit. So many of our space-based, projects, particularly the larger ones, are international collaborations. We heard there was a whole session dedicated earlier to international collaboration, but space brings kind of its own unique challenges, right? Many of our technologies that we use have military applications. Those bring about restrictions that governments impose. I know you've had some experience working on international space-based projects. Can you talk about what the primary roadblocks for those are, particularly in the context of the Astroinformatics?
Yeah, I have primarily worked in space science. And for us, one of the major international collaborations was Chandrayaan-1, where we had payloads from both NASA and ESA on the Chandrayaan-1 satellite. And we now have a major remote sensing satellite coming up, the NISAR, which is with NASA. One thing I find challenging is that while remote sensing and communications data are revenue producing, astronomy or science data is not commercial. And so at the same time, they're very demanding in terms of both resources in terms of computation and at the same time in terms of storage and archival. So to convince the management that this is indeed very useful, as it might provide pioneering ways to actually improve our data astroinformatics capabilities, is something which I found we had to do. And the second thing was where international collaboration was very, very useful was that in data processing, data archival, where we do use tools developed by scientists all over the world. We do use the CDS of the Strasbourg, Aladdin, Vizier, etc. We use the HEARSARC tools of NASA for the X-ray processing, X-ray data processing especially. And so we are extremely appreciative of the capability of astronomers to actually share whatever tools they develop internationally so that everyone doesn't have to redevelop the same thing. And that's, I think, one of the things of international collaboration, which we have to emphasize maybe to the government agencies and so on. They would already know, but sometimes it's good to reiterate that. And at the same time, I think we do need policies to interface at academia level, academia to agency level, and agency to agency level. Agency to agency level does exist, but it's a little formal. Whereas when we interface at academia level, it's a little more less formal and therefore easier. But it still has to have the sometimes it has to have the clearance of the agencies, because we are working with satellites which are owned by the agencies.
Those are some great points in there. Thank you very much. You brought up, industry and how there's some potentially commercial application for things like, earth science, earth observing kind of satellites, or that necessarily isn't the case for astronomy data. If you flip that around, Dan talked about, potential ways that astronomy could benefit from progress in industry. We've heard a lot in the news about, language learning models, ChatGPT, DALL-E, all of these. So since Dan talked a little bit about this, I'll ask Richard, how can we best capitalize on these developments to enable space-based discoveries, specifically in astronomy?
Specifically in astronomy, so that gives a focus for the question. Let me approach it. First of all, we're all aware of the burgeoning of new space or commercial space, and that's a huge part of the future that we all can see. So the AI capabilities based on large language models, et cetera, those have been getting a lot of attention recently. We're all aware of that. But I would also point to certainly in the earth science arena, the advent of the new kinds of commercial data providers, Planet Labs being just one example, but there's many more. and even more so internationally. So I think that is a game changer in terms of when we think about the data challenges, and this would apply to any science disciplines, including astronomy, that what the data sources are not going to be the traditional, government projects that put either large telescopes in space or Earth observing assets, but increasingly it's going to be coming from the commercial assets. And so that's a shift, but also ups the ante, not only in terms of data sourcing, but also ups the ante in driving home the point that it's really all about being able to integrate and effectively work with all kinds of data sets from many sources, with all the curation, formatting, processing problems that implies. So that leads us back to standardization type questions again. As far as the role of the emerging AI capabilities, there's some pretty impressive technologies that are emerging there. There's also, as we know, a bit of misinformation out there. So without getting into it too much about what the capabilities are and are not, I think just picking ChatGPT, not that it's sort of representative of a class of these capabilities, that there's always going to be a responsibility on the user of such capabilities to both validate what's coming out and then to use it responsibly. And I think all of us should make that point as often as we can and in many contexts as we can, because I think that's kind of fundamental in the kinds of misunderstandings that are out there. And anyway, I'll stop there. I'm sure Dan will have some insights on this topic as well.
Yeah, if you want to add anything, Dan, go ahead.
I think Rich did a wonderful job. The thing that I continue to tell people is, we're training a statistical model. We're using math to figure out how to string together and extract information from these large language models. And so, we use it as an informed user, as Rich said, right? And it's an assistant tool where it's not meant to replace the scientist. And I think one of the things that we're seeing, and we're seeing this in multiple discipline areas to make that point, is we should see these kinds of tools as opportunities to help gain insight, but not as being factually correct.
Okay. I'm glad that Richard brought up standardization, because that was certainly something came up in Dan's talk as well that I wanted to make sure we asked about. So I think I'm going to ask this to Laurent. This is so important for dealing with heterogeneous data sets, building off of some of the VO and IVOA efforts. What do you think that astronomy has done well in the past when it comes to standardization, and what should our field be doing better in the next decade?
So this is a very tough question. I think there was these different VO initiative, and so the format, and there are, as I was mentioning before, there is this that people who are developing these solutions should go hand in hand also with the astronomers who are doing the research, because the tendency is sometimes that it's dangerous to try to do good for others. So that's a general lesson to be learned. But we see that already in the past, to have the question of merging catalogs, names, and sources, it has been enormous effort simply to identify the same source. So such initiative like the CDS has been extremely useful in being able to a bit homogenize. There is one example that I find so amusing that I tell to the student I'm teaching to, is about a Cepheid called LCAR. But the L is, you know that you have the denomination from the Carina constellation, the L, but you have also the Iota car. Iota is a little I without a point, And you have in the literature a confusion between these two different stars, which are taken as the same one. And so I think there the CDS has been enormous. I learned recently that there are 2 million queries per day. We see that the generalization of these use is a huge success. Also, the question of format, as I was mentioning earlier, had a big, you are able to exchange data in different format so that you can use the Gaia archive, download data, and then use, for example, Topcat in a very smooth, extremely smooth way. I think there that has been a huge success. And obviously, what we should try to do in the future is to develop more of this. Also, this question of interoperability of different surveys and merging the data. For example, in Gaia, we saw that we combined around 150 catalogs of variable sources. I think that's one of the largest efforts that has been done up to now in the literature, to take the big variability catalogs. And then what was good with Gaia is that we could look at this data on the Gaia perspective. So such surveys like Gaia, which are really all sky global with high dynamical ranges, suddenly they can fix a grid in a way for the other surveys. So that's I think the large surveys, large effort like this is extremely good for astronomy.
Yeah, we certainly see, some of the you mentioned CDS. I think that's a great example. We have a number of examples, in the US that I can think of as well, like, NED, the extragalactic database, SINBAD also in Europe, these things that are so fundamental for the way that astronomers work, and becoming more so as we get more and more data, but maybe don't receive necessarily the support that they really, given that the importance that the infrastructure has for our science. I think that's a great point to bring up. Let me switch gears a little bit and ask Sita a question. One of the things that Richard brought up that I definitely wanted to talk about is the proliferation of, commercial space utilization. We see this, commercially, we see it, educationally, scientifically. Low Earth orbit has just been democratized in a way that, it was definitely not 20 or 30 years ago. So I want to ask in particular about, education and public outreach. Seems like a great opportunity to bring students, to train them, to get them on board. And I know there have been lots of efforts going on internationally to do that, but where do you see all of that going in the next 10 years? And how can we better motivate the public making use of these great new capabilities that we have for access to low Earth orbit? If you're speaking, Sita, we can't hear you. You're still muted.
As far as outreach is concerned, I think it is essential. I mean, considering that not only that we spend a lot on astronomy missions, but it's also that astronomy is a very, very exciting, not only for the students, but also for the public. So that being the case, it's extremely important that we keep the outreach component in pace with the missions which we fly. And missions are getting more and more complex, and therefore it's outreach efforts are also going to get more complex, because we need to, while we need to simplify what we do in space, at the same time, we also need to convey the complexity of the particular scientific mission. So that those two have to be taken together. The other thing is, while the students, etc., are very, very excited to start with, but there are several students and postdocs who work with us, and also including engineers who work with us on developing the data pipeline, data dissemination, data archival, and so on. It has been a difficult task to keep them motivated, because they don't get the same opportunities to attend conferences, to attend meetings, etc., as the scientists do. And so at some stage, there is a break off. So how do you keep them motivated? How do you keep them, how do you keep them exchange ideas between teams internationally, and at the same time within the team, if they have to leave, how do you hand over the baton to the next team members? These are some things I think which we can exchange across the teams. And for example, the PDS format for planetary data has been one great example where that has been developed, and it has been disseminated to various members of the space agencies, and training schools have been held so that the users also absorb the data format and they create the data in that format. So I think these are all aspects which has to be covered, not only in outreach, not only in citizen science, etc., but also in the team amongst the team members itself, who are not necessarily the scientists who use the data for purely science purposes.
Thank you for that. I wanted to bring a couple of questions that we got from audience members during Dan's talk, because I think it'll be good not just for Dan to answer, but also some of the other folks in here might want to weigh in. So I'm going to read this. This was from Alberto Crone Martins. It says, thanks for the nice talk. How do you see open hardware and software initiatives in NASA and ESA? Hasn't forcibly public software licenses such as GPL posed problems in the past for space agencies? Maybe Dan can take that one first, and then Laurent can weigh in on the ESA side of things.
Yeah, so it's a very good point, and I know NASA is continuing to work through that as part of that question on software licensing and so forth as part of their open science initiative. I know at JPL we focus more on the Apache version 2 license, partly because it provides a lot of downstream freedom to begin to modify software and so forth. And so I think the intention, I know of NASA is really to try to make sure that that software can be as freely disseminated and leveraged as openly as possible across agencies. And this is probably an area where internationally we could work together as a community to make sure that the right access and use of software is there, and that there are no sort of requirements that are placed which would limit its extensibility and use across agencies. But I know that when a PDS was mentioned, I know that we have shifted all our PDS development and tools to be developed as open source now, and it's being done in GitHub. We're using Apache license, version 2 license, so forth.
Okay, great. Laurent, you want to answer on the ESA side of things?
So I can answer on the Gaia side. So the point is that the software that has been developed for Gaia is in Java. So that was requirement of that we received. And so the software will be delivered at the end. So will made public, and that will be open source. So I think that's it's also linked to this provenance problem that or question I was mentioning earlier. You want as the data went through a lot of transformation, then you need to know well, it's good to give the software by which it was produced. And so also what is happening is that we are using several software like classification models like H2O. So also when we integrate things, we need to be obviously careful that it's also open source.
Excellent. All right, well, we're coming up on the end of our time here. I thought maybe I could give everyone a minute or so just to wrap up with any parting thoughts they wanted to share, or if there are any quick topics they wanted to bring up that we didn't get to touch on. So Richard, why don't you go first?
Yeah, thanks, Brad. It's something we discussed briefly, and I know I've had this discussion with both Ashish and Dan as well. The focus of the discussions here are primarily astronomy, but I think we can also open it up a little and look at planetary science and earth science, and note that the three science areas are in slightly different parts of the, I don't know how to put it, the life cycle. But that means there's an opportunity for them to learn from each other. For example, planetary is still in a kind of a fundamental discovery and characterization mode about what's even out there. You know, every time we go to a new object, we are always surprised by new phenomena. And so it tends to focus on discovery type techniques and change detection and those kinds of things. Astronomy has been, I think, as a field, often leans on classification, and that's been used effectively in many different contexts. And as we've noted a few times today, the astronomy community has done a fantastic job of starting to move into the realm of standardization of data formats and that kind of thing, and really showing leadership. Now, in earth science, there's the most data of all, and arguably the things have reached the point where there are sophisticated models, and a lot of it's about model prediction and analysis. So that's a slightly different paradigm as well, and emphasis on things like uncertainty quantification are very prominent now in earth science. But I think ultimately all three science disciplines will touch all of those areas, and it doesn't really matter which area got a sort of a head start, if you want to put it that way. We can all lean on each other, and we can all learn from each other as we all grapple with the challenges of how to apply data science in our different arenas. Thanks.
That's a great point. Thank you for bringing that up. Sita, any last points or parting thoughts you wanted to share?
Yeah, there are many astronomers. I wouldn't say astronomers, actually, those who have worked on data of astronomy, going to the industry, sometimes as a career itself. Whether there can be something in a return from industry to astronomy. We have found that if there are some industries who realize the pioneering efforts of astronomers and therefore would like to work on astronomy projects, if we could get more and more of that kind, because as I said, astronomy is not commercial, and so the projects couldn't probably pay at the same commercial level as the industry demand. So ways to actually get industries to contribute to the software and data science part would also be very welcome, as they are contributing in the hardware development and detector development, etc.
Excellent. We should definitely make sure that gets into the white paper that we are working on. Thank you. Laurent, go ahead. Parting thoughts.
Yes, I would say that as an astronomer, I find nature is amazing with immense diversity, and we want to understand the universe and the constituent of the universe. And through the different experiments or surveys or data we acquire, it's getting quite complex. So in a space mission like Gaia, you had people from the industry, space industry, developing instruments which are very complex. You have to group scientists together because no institute has all the knowledge to do the analysis of Gaia data. You need to have also computer scientists with a very different competences. And also you have the population through, for example, citizen science projects. We launched one on Gaia, and we see it's useful. So you do really the progress in science when you put all these people together. And I find this is, maybe I'm idealistic. I see that science is able to bring all the many kind of different competencies to gain knowledge about our universe. And I find this is really amazing. What well, we should stay humble. When you study the universe, you are forced to be humble. But still, I'm amazed by all this effort, and we really advance in knowledge. And that's to participate to this is a fantastic feeling.
Really good to remember how fortunate we are, to be part of this great endeavor. Thank you for ending on that. And Dan, I'll give you the last words before we turn it over to the next panel here.
And thanks to you and all the panelists. I really think that these kinds of venues are important because we need to work together and we need to work internationally. And I see the question in the chat from Alberto about what about space nets and how do we get sensors to be able to talk to each other across international boundaries. So both in space and on the ground, these are to me where we need to go to figure out how to continue to leverage our observations and our space assets together, and to be able to ensure astronomy is done as a collaborative activity. So it's connecting our space assets, our archives, sharing our software, sharing our data. All of those things I think are going to be really, really critical in the future. And I think the area of I'll end on is the rising tide opportunity of artificial intelligence and machine learning, looking at how do we harness that together internationally, and what does that mean? I think is there's an opportunity for us to have more conversations and develop more of a roadmap around that.
All right. Well, I will say thank you all. You've been a fantastic panel. Appreciate it. And I will turn things back over to Ashish and Pranav.
Brad and the entire panel, this was really good. And he also kept it to time. Gained us back 5 minutes, in fact. That's wonderful. Thank you so much. And as you said, we look forward to incorporating the comments that were made during the panel back into the white paper. And yes, let's move on to the last panel of the meeting. And the meeting is about astroinformatics, and it's fitting that the panel is also on astroinformatics. So Matthew will be moderating this panel. Matthew, welcome. Welcome to the other panelists. You can introduce yourself and take it over.
I'm not seeing all the panelists yet, Ashish.
Okay, so Francisco should be joining momentarily, and so should Alberto be joining.
And
I'm
Ronaldo?
not sure about Ronaldo.
Okay.
So give them a minute, maybe.
Yeah, let's give it just a couple of minutes, and we'll make a start.
We can take a 5-minute break and then we can start. We can also
let's take a 5-minute break and then start. Hi, Alberto. We're just waiting for all the panelists to join.
Hey, Alberto. Long time no see.
Hello, live long and prosper.
I think Francisco may have the wrong link because he says he's waiting to be let in, which should not happen. So let me send him the link again.
Hello.
Hey.
Yes, I was in the wrong link. Sorry.
Okay, so I think that's probably everyone we're expecting for the panel.
I think it's been 4 minutes anyway, so you should be able to start.
Yes, so let's make a start. So welcome everyone to the final panel of the of today, at least for this S20 session. And the focus of this panel is Astroinformatics for Sustainable Development. I'm very pleased to have 4 luminaries in the field as the panelists. In no particular order, we have Alberto Krohn Martins, who's a lecturer in informatics at the University of California, Irvine. Francisco Förster, who's a professor at Universidad de Chile and involved in various mathematics and data science institutes at that institute. Giuseppe Longo, who's a professor of astrophysics and data mining at the University Federico II in Naples, in Italy. Yes, those are our 3 panelists. And Ronaldo, who should be here, but hasn't joined, unfortunately. So what I would like to start off with is a sort of a basic question for you, which is that we've heard, particularly in the last couple of panels, about that there's been much international effort over the last 20 years, or even further, in coordinating the management and curation of and access to large astronomical data sets. And that's particularly going forward both from space and from ground-based observing facilities with things like obviously the Rubin Observatory and LSST in the optical, but also spectroscopic surveys like Sloan 5 and DESI and the big radio surveys that are coming. So on the sort of data infrastructure, there may be moves towards international cooperation and whatever. But what do you see as the biggest challenge to actually using these data, particularly for researchers who are not maybe in the first countries? And what is the one thing that you would propose to overcome these challenges? So let's start off with Francisco.
Thank you. Well, it's a difficult question. I can tell. I mean, how we use different data sets. I'm the PI of the project called Alerce. So there is a broker for the Vera Rubin that is also processing data from the CDF and Atlas. There is different telescopes, and we have to cross-match this data in real time and provide information, annotate the data with all the information that is available. I think the general use of APIs, so the more general use of APIs will be really welcome. So some of us are used to it because of this is what we need. So we have learned from our needs, but not everyone in the community knows like the simple access to APIs and how to create one and how to document it well. So I think that will help a lot. But then you have perhaps another level of problem, which is coming, which is what if I want to access a lot of data? And maybe then APIs are not the solution. Maybe in that case, you need more centralized data and processing platforms, for example, like the Rubin Science platform, the NOIR Lab, Data Lab. So these will be my two suggestions: to centralize processing and help interoperability through APIs. I mean, this is nothing new, but to make it more widely used.
Okay, thank you, Francisco. That gives us a couple of points we can come back to in a few minutes. Alberto.
Okay, thank you. So Francisco was talking about APIs and how to use APIs, and not everybody knows how to use or how to create an API, right? And I think that one of the biggest problems for those curation and access of very large astronomical data sets and how for people to use and to make good science out of this is education. And like the usage of APIs is a part of the education, right? So at the same time, that's like when we look to how people are being educated, at the same time, it seems that people and like astronomers are being less and less educated in fundamental mathematics and physics stuff, but they are not being well educated in the computational side of things. They are being educated how to write simple scripts in Python or like to do simple Jupyter notebooks, but they are not being educated at fundamental of like algorithms, how to think, how a computer works, right? Or discrete mathematics, or there is a lack of education, and that is even dangerous for the future of the entire field. Like I would say of the entire astroinformatics field, because it needs to be interdisciplinary. So people needs to know how to communicate together. We need to define languages so people can talk between the different fields, right? And I think that this has been one big problem in to use and to make good usage of those very large data sets that we have nowadays.
Thank you, Alberto, for that opening salvo. And Pepe.
Say that there is very little to add, just one consideration. I mean, you spoke about the large international effort in defining management, curation, and access to the data. And I am afraid that while a lot of work has been done, many problems which are encountered by people, let's say, not involved in large projects, not in, let's say, less technologically advanced countries, is the fact that these standards are not adopted in a very effective way in the astronomical community. The large surveys usually do it, the large data centers usually do it, but most of the data still have not yet been made fully interoperable and fully standardized. And this somehow creates quite a lot of confusion in people. So I think that is also one thing which needs to be addressed. I mean, the community should be forced to adopt these standards, and this will also, this will make much easier also the transition which Alex was mentioning today from data to artificial intelligence ready data, because you need to have much more homogeneous data sets. I think this is a problem. And another problem is in the distribution. I mean, Francisco and Alberto speak from the point of view of technologically advanced countries who are involved in large projects. But if you are outside of these countries, you have a huge problem in accessing the data and in exploiting them. And These we encounter every day with our students around the world. I mean, that is a big problem. I think I have not much more to add on this topic.
Thank you, Giuseppe. Actually, this brings us to, I think, a good next question, which is as you've identified that developed countries, particularly in the astroinformatics field, have a very clear advantage in access to resources or an access to the resources that are needed to support these types of activities that we're talking about, where we're talking about, these terabyte or petabyte data sets that we're interested in doing things with and transferring them around or having large computations running at them. And our natural inclination is to look to government or look to governments and to institutions of that type for support in building up the resources for us to enable the science. But yesterday saw the release of Threads by Meta, and there are these other big multinational data science companies out there that we use all the day, Google, Amazon, et cetera, et cetera. And the question is, as we move further into the 21st century, do you think that they have a significant role to play in supporting these types of science activities, or that they should be, or even that organizations like the G20 can put pressure on them to support these types of science activities, which we claim are for the betterment of mankind? So I'll let Alberto go first because he's smiling at this one.
Oh, Matthew. Okay, so that's a very good and very hard question, by the way. About the G20 responsibility, I don't know, but what's the responsibility of a company when you think about a company, right? Normally, when you think about a company, the first responsibility is generating revenue, either now or in the future. At some point, a company needs to generate some sort of revenue. So, and then it becomes how you quantify and how humankind quantify what's revenue of a company, right? If it's only money, it's very hard to see how a company could be a significant contributor to future developments or in large scales. Obviously, there will always be, and if the resources that the field require is small compared to the resources available for the company, then the company can even profit and perhaps monetize on their corporate image out of the small contribution that they are making to the field, right? But in very large scales, except if the company sees perhaps in the development of a database, like Microsoft is thinking about improving the SQL Server database. So they help funding Sloan to develop the technology they are going to commercialize in the future. I see that's hard to, if the contribution needs to be large compared to the resource of the company, then I feel that it's hard for the company to actually contribute to it. However, at the level of something G20 or S20, so what perhaps is missing to leverage a little bit the field between poor countries and richer countries is to have some sort of worldwide science funding agency, right? Which is obviously missing. And this helped a lot Europe to integrate themselves and to all the countries to leverage since World War II until now. The European Union, the start of the European Union, and having the European Research Council and everything, forcing different countries to work together in projects, helped even to level the field between poorer and richer countries in Europe itself, right? So perhaps something like that at the level of the world could help to leverage the field in the future. That's what I think.
Thank you, Alberto. Francisco.
So see, I think this is much harder than the last question. Yes. So yeah, I think the reality is that the industry is moving in the cloud and using these services. So I think from a selfish point of view of these companies, they can train people that are some of the best minds, let's say, to learn how to use the services. But I mean, so in that sense, they will benefit if they help science make progress, let's say. But of course, there is a risk to be captured by these companies the same way we're captured in a way by, let's say, journals, let's say. So we like editorial because it helps us to guarantee the quality of the research, but then prices start go up and you leave half of the world out of this editorial process, right? So I think it kind of, there are some similarities. And perhaps one way to solve this is to, for example, to incentivize ways to move to open source, and if you use some cloud service, make sure that the tools that you use can be easily moved from one cloud provider to the other, for example. So I'm just trying to think of ideas, but it's really a hard problem. Yeah, so help people not be captured by one individual company, and from their point of view, they will benefit from training people using their services.
Pepe?
I think both of you made very good points. I think that for sure these companies need to play a role in what's happening, because it is unthinkable that all governments can access supercomputing resources. This will not be sustainable in terms of electricity, of bill, of environmental impact, and so on. Think only to the fact that almost 10% of the CO2 is produced by the training of the large language models and so on. It's really, or for mining the bitcoins. I mean, so it's just unthinkable that governments can sustain what we need. So I think that somehow large companies needs to be involved in the game. And in the past, they've shown that they have a sweet tooth for astronomy, also because astronomy on one end provides access. It was more true in the past than it is now, but it provides access to complex data with no economic strings attached, so they can use it for testing infrastructure and so on. And also astronomy helps them to clean, let's say, their image in somehow. I mean, you know, if we have this advantage that astronomy is beautiful and it's very popular, and therefore, you know, to contribute to astronomy helps cleaning the image. So from the sustainability point of view, I'm sorry, but since a few years, I'm very much into what we can do to help other less fortunate countries in entering, you know, on a more even ground of the field. I think that what we could do as a community is as International Astronomical Union, for instance, or at the government level, is to force this company to provide free access to, for instance, their computing infrastructure to students in less favored countries, like, for instance, Microsoft Azure, Google Colab. I mean, this will be a real way to spread the astroinformatics, let's say, but more general data science also in other countries. And to tell you the truth, it's also the only way I see it in order to democratize the process, because, you know, it's my recent experience with more than 300 students every year coming to study data science from all over the Far East to Middle East and Africa, is that their level of preparation is very different. And before entering a normal master, they need to, let's say, to be leveled in the level of preparation. And they have difficulties in doing so. So I think that because just their background is completely different. So in theory, in an ideal world, I mean, there should be an effort to make these companies more involved in the educational process of the people. and providing at much cheaper price their computational resource. I must also say that many of these countries, it's difficult to have access to free information. Try to imagine to have access, to free computing resources. I mean, so it's a huge problem what we are addressing now. I mean,
Yes, no, I agree that.
Alberto wants to say something.
Alberto?
No, please, Matthew. You agree? You agree? Continue.
No, I was about to say I agree with Pepe's comment about the freedom of information or the freedom of access to information is difficult. But the onus is maybe on those countries with resources to make as much available as can be made available, and then that at least removes one hurdle in the access for less advantaged or less well resourced to be able to get to what they need to get. But what was your response going to be, Alberto?
Oh, it's not a response. I would just add to all of this because like there is another level also of like of advantage in a certain ways. That's like countries with more resources they're always going to have, and even in countries with good resources, even among European countries that we see, which is like in certain countries the universities are seen as teaching only or teaching focused institutions only instead of teaching plus research and research plus teaching going together, right? And this puts a burden in the professors and the researchers where like those professors they will end up teaching 80 or 100% of their time, while in other countries they are going to teach 15% or 30%, or when complaining about a heavy load is 50%, right? And this is like a culture problem that's probably not going to change in the foreseeable future. And in most poorer countries, the universities are seen like that. So it's not only having resources to do the computation or doing resources to access the data, it's also having time resources for people to think. And this is lacking in many countries, right? And this is something that at the level of S20 or G20 can be discussed also further.
Yes. So I mean, something that's coming clear, I think, from what we've said so far is that it's this question of education, and our individual countries have their own education systems, but there is within the field of astroinformatics, we can define, what an education program based around that, or what are the requirements that you need to be able to carry out a successful astroinformatics based research project, let us say. That can be within with the assistance of both national and international organizations, as well as private organizations, which may see that it is, there's a philanthropic element to supporting that sort of activity. And the question then becomes, exactly what we need to define on that. And I think one thing that maybe comes out of that is that, I mean, I was looking at my news feed earlier this morning, and there are at least 3 new exciting astronomy discoveries right at the top. And as Pepe has said, astronomy is that sweet spot science that really grabs people. I mean, there are people who obviously are interested in medical things, and there are people who are interested in geology and physics and all the other sciences. But astronomy seems to be the one that grabs the regular person in the street most. And if you got a good astronomy story, you guaranteed at least a little slot in the 24-hour news cycle before the next one comes up. And though we have concerns within our astronomy field that, once we have all these big discovery engines online, they're all going to be competing with each other and they're going to overwhelm. I think, there's a slot thing. So what I'm curious about is, can we capitalize on this, particular within the field of the sort of stuff that that we do with the astroinformatics? And where do you see the sorts of things that we do potentially having bigger impacts, building on that and going out into society more generally whether it's interdisciplinary, or are there more social impacts, things that we can drive from that sort of work, or the work that we do. So let's take Pepe first on this one.
Well, this is a sort of catch-22 question. Let me tell you why. Because in the early days of the virtual observatory, I still remember a statement by one of the founders. The virtual observatory will become a success when people will use its tools and its data without even realizing it. And so basically, this is, what you are saying is killed at the beginning. I mean, because basically, if you speak about public recognition of astroinformatics or astroinformatics success, astroinformatics is the embedding of technologies in machine learning, computer science, data engineering, this type of thing. So it's something which is behind. And it is very difficult to assess, because what you get at the end is a scientific discovery. What breaks news is the scientific discovery itself. And basically, the way you have obtained that result just goes in one line. So I really don't see how we can, capitalize on that.
But the scientific discovery is the end process, a lot of development of methodology and infrastructure.
But I agree on that. But on newspapers,
yeah, I mean the newspapers
doesn't get anything of it. So I mean, on a more professional level, I think that we need to act as a community in order to emphasize the role played by people who write methodologies, not only software, but really new methodologies, new statistical, new machine learning methodologies to solve complex problems. But this has been a long-lasting problem, which we have been discussing at the Astroinformatics meetings for the last 12 years, I think, and no solution came out of it. I don't know whether I answered your question. But...
No, I think you do. I think that you've highlighted that a way to drive this sort of thing is maybe, as you say, for there to be more of a community on the methodology side, which we don't necessarily have at the moment. We have some international organizations which try and focus on that, but they're very ad hoc. And if there was maybe more of a formal support structure, though that can always be the death knell of any organization, as we all know. But so the thing. Let me pass to Francisco.
I mean, it's obvious that astronomy is really news catching, that it catches the attention of people, and we should really, capitalize. And it's possible. I mean, one thing that has happened in Chile that I've seen a huge change in the last decade is that all research initiatives that get funding, they are forced to hire a journalist, full-time journalist, dedicated to public science, let's say, to spread the news and that speak the same language as the people working in newspapers and the TV and so on. And astronomy is everywhere now in the news. Sometimes we have even seen astronomy news in the cover of a newspaper in Chile. I think this is not common in other countries. And Chile, I'm from Chile, and we have all the telescopes, so it's kind of special. Astronomy has a special role in Chile. But I think something similar can be done in other countries. If you make sure that you have a full-time journalist talking to astronomers, talking to the press, and helping this communication. So, and how many people do you know that was inspired by Carl Sagan to do science? I know a lot of people, myself included. And he was an astronomer that was able to communicate this love for knowledge and in a way helping more people into STEM fields, let's say. So I do think we have an important role to play in this respect. And the discoveries are key.
So let me push back a bit on this one. Yes, when Obama stood up and talked about some science discovery, that got people's attention because you have the President of the United States talking about a science discovery. The question is, you know, yes, we can get these things into the news cycle, and that's the first step for us because it gets our material out there and it gets people engaged and whatever. The question is then, how do we, you know, can you think of ways we can then move that beyond just, oh, this is good, this is interesting for 24 hours. You know, we need to get the politicians thinking, well, we should be, oh, well, is that the only thing we're doing, or is there more that we should be doing to support that?
You know one example as well in Chile, where the Congreso Futuro, which is like a meeting, I think Pepe has also been there, I'm not sure.
Yeah.
That is organized with the parliament in Chile, and it happens once a year, and you have the general public and the politicians in a room talking about science. And this has helped a lot, I think, to also to bridge this gap between science community and members of parliament. Of course, more needs to be done. If you listen to members of parliament talking about science, you clearly need more education. But we need to keep pushing.
Well, yeah, I think we're all in agreement on that.
Yeah.
Well, okay,
I just want to add a comment. I mean, it's strange that we are a community of people at the forefront of technology, but in terms of advertisement, we still think in a very old way. Today, more than any journalist can do a good YouTuber. And that is what I think we are missing. I mean, we are not where we could improve a lot, especially in astroinformatics, to start building a community of people who exploit the new media like YouTube, Instagram, even TikTok. I don't like TikTok, but you know, to communicate the discoveries which we make, and also, you know, I'm focusing on astroinformatics more than on astronomy, because in astronomy already people are doing that, not very successfully, but they're doing it. But I think that is a very good venue to follow.
Yeah, and the journalists are the people that are pushing this, at least in Chile. I've seen it myself. So they're pushing for TikTok, and astronomers say, no, sorry, I don't want to be in that.
So, Alberto?
Just to continue this astronomers, oh, I don't want to be in that. There is also perhaps a problem within the astronomy field as well. Like, as originally I'm a trained astrometrist, astronomer by formation, but now I teach computer sciences in informatics, information and computer sciences school, right? And I have many students who come to me. They are computer scientists, they are mathematicians even, who want to do astronomy. They want to work in astronomical problems. And this is perfect. So they do their undergrad work, but when they want to continue and apply to PhDs and masters, we don't accept them in our field, which is a big problem. So they stop their training as well. Like they start gathering information on astronomy, but then there is a door where it's blocked for them because astronomy is within the physics department that doesn't accept anyone but physicists, right, in their PhDs. And this is a big problem as well. And this is probably also harming a little bit our like communication, like beyond just, okay, this is a pretty picture, right? The pretty picture thing is easy and quick to do. The long-term things are harder to do. And perhaps there is also some fault on our side on this. So it's very similar to, I don't want to be in TikTok, right?
So that's an interesting observation, because it suggests that there is a place for, so, you know, if we say that the well-resourced countries in the world have a very traditional view of what's required, and, you know, are maybe slow to accept the new methodologies, and it's hard for capable students to find places where they can get the education required to bring them up to where they want to be so that they can be professors and lecturers, that places which are more flexible, because they may have already a less developed program at the moment, could accelerate to be the front. And I think Chile to some extent has done that. I mean, Chile is, you know, one of the leading places for astroinformatics, I think, worldwide these days. and maybe was not so much 10 years ago. And I wonder if there is scope there for, maybe there's a type of activity, if you're talking about sustainable development, where you could anticipate an international program which is supporting that sort of thing. Again, we keep coming back to this idea of education as well, as maybe one of the places where most impact could be made with the right incentives. So I wonder on that.
And just to add on that a little bit, Matthew, so it's education and it's everything that go around education, right?
Yes,
because like
exactly.
with education, you need funding.
Yes.
And like different countries will have different funding levels for the students. And with education, international education, you need the students to be able to travel around,
yes,
which is a nightmare. Like as a Brazilian who lived in Europe and in the US, I can say it's a nightmare, right? You are fighting against the system every single time and every single year, right? And like if you want education to flourish, you cannot have those barriers, right? So like visas for students should be easier to get, and easier to get and easier to maintain, right? As well.
Yes.
So and everything
But
around.
in our wild dreams, we could anticipate that the G20 sets up a fund for international astroinformatics education, and that the state departments or the representatives of each of those countries agrees on easy visas for members of that program.
Can I comment on this?
Yes, please.
I think that if for sure the G20 can do a lot on that. Europe has been doing a lot on that. And also, in Europe, the situation in some sense is more flexible than what is in the United States, because, for instance, interdisciplinary programs are more easily funded, and there is much more attention nowadays in what is called the digital Europe. So that's for. But what I think it will be to establish connections with other communities who have much more economic and political power than we have as astronomers, but they are entering the same arena. They have the same problem. I'm talking, for instance, on biological community, on green economy community, ecological community, physicist, high energy physics community, and so on. And I think that we could make a statement at the government level to favor the education in the fields of data science, scientific application of data science, machine learning. And there, we can carve our slot for astroinformatics, then bioinformatics, and so on. But it should be, this process should start with the interaction between the international professional companies. And it would have much more weight that we can have as astroinformaticians or as astronomers alone.
That's a good point. Francisco?
Yeah, can I add something? Perhaps it's not exactly the same, but I've noticed something recently. I'm not sure if you've noticed the same. So there has been a push. So education covers like finding the best talent and educating in the best institutions in the world, normally in the richest countries in the world. And for example, you've seen that the GRE test has been eliminated from most universities because it was very expensive and kind of was seen as unfair. But what we have seen in Chile is that this is having the opposite effect. It's more difficult now for Chilean students to be selected for the top universities. So it was with a good intention, and what we're seeing is that students are finding it more difficult because it's kind of less objective now. So this touches on the point of education and global, let's say, distribution of education. So I don't know if you have any comments on that or you've seen anything. Yeah.
Yeah, I mean, this is the GRE got abandoned as a post-COVID or as a COVID measure because there was not an equality on the boards. Largely, I think there were, there's been lots of complaint about it beforehand, but it needed a pandemic to actually push it that way for colleges in the US. but I think you're right that there is. Yes, it's a difficult. Yeah, I'm not saying I have an answer. I don't know if any of the other two panelists have an answer on this one.
We have only problems in that direction. I mean, there's no answers, unfortunately.
Yeah, it's the answer to that's very hard. On the other hand, probably to link with like something that we will discuss in a few minutes, education can also be helped by new technology that's being brought out now, right?
Yeah. So thank you for the plug onto our next question, which is actually, as we're all aware, the rise of large language models such as ChatGPT and such is, depending on your perspective, either the most exciting or daunting development in AI in the last year. I note that there's a news item on the BBC this morning, how 5 ways AI will kill you in the next year or something like this. And there've been great debates online and offline about whether we are heading towards general AI or where we're heading. I guess, as experts in the astroinformatics field, firstly, do you think that these sort of models will have a significant effect on what we do in the next few years? And are there possibly specific focused developments that we could identify that could be, good for sustainability? And on that, how do we guarantee again that everyone gets an equal share of the pie, that it's not just those who can afford the fuel bill which is required to train these large models, that we do have equal access to everyone to understand how they work and how they can apply it and maybe regulate it if that's needed? So let me start with you, Pepe, with you, Alberto, rather, because you were heading that way anyhow.
Okay. So I feel it will. Like it's very hard to be certain at this moment yet, but I strongly feel that there will be a big impact. Not necessarily with the simple models that we have nowadays, which are simply like predicting the next token in a series of tokens, right? Well, at least up to the ChatGPT 3.5 and things like that we had, they are still relatively small models, and they have little to no real abstraction capabilities, right? They are, again, just predicting what comes next in a series of tokens somehow, right? However, like given the sheer size of those models, if you can train very large, if you have a very large memory, and this is starting to happen with GPT-4, like, and beyond that, if you can link what are those chains are directly to what a computer can calculate, and with data sources as well, right? And it's not just predicting like a series of tokens. Then it's already starting to be able to do things that are much more interesting and like perhaps much more abstract as well. Like especially if you start linking more and more with unsupervised learning, right? But again, like one thing that I do believe that it's a good usage of those models nowadays, and we are starting to do this in most universities, I believe, in the world, at least in most well-funded universities, is to use those models in education, not ignoring them, because like students are using them, like some students for the bad reasons, many students actually for the good reasons. And the way that they are using them is to actually help them learning as well, right? So at UCI during the summer, together with 4 PhD students, we are building a system that links previous assignments for several computer science courses, the prompt of the assignments, to help to create AI-based tutors. Like, so the model, so the language model can help scaling education as well, right? Obviously, it's not going to be as good as, at least not in the foreseeable future, as having a professor there or having human TAs there, but it helps scaling, right? Like I last winter I was teaching 600 students in one class. Next winter it's going to be 800 students. I have an army of TAs, but even with the army of TAs, it's impossible to provide individualized attention to all the student assignments. Like with language models, we can do things like that. so we can take education. Again, it's not as good as having a professor in the middle of the Amazon forest, but we can have at least a good level of education being offered in a more widespread way. It's very similar to like listening to music over a CD or going to the orchestra house. It's better to go to a concert hall and to listen to the real orchestra, but it doesn't scale, right? The CD or the streaming service scales, right? Even if it's not as good as, you are taking and you are empowering more people to access information and to be educated, essentially, right? So,
Francisco.
I agree with what Alberto said. It will play a big role in education, and it's helping us. I mean, educate. I'm educated by these models now. I'm asking questions about programming. I use it every day. But I also see like an important use in the first point of this panel, and how to work with heterogeneous sources of data, how to normalize, let's say that, to standardize. I think they can play a big role. Dealing with complexity, and also enabling and the access of the scientists and students to different services. So usually there is a steep learning curve that you need to go through every time you enter a new data set, let's say. These large language models can help you. For example, translate natural language into all the individual steps that you have to do to answer a scientific question using some data. So, but what I think would be ideal is that as a community we work and try to build large language models that are more science aware. I think this could be done by our community, and slowly but steadily try to include causality in these models and try to force it somehow, more than just predicting the next token, as Alberto said.
It's my turn.
Yes.
Oh, sorry, I deactivated the speaker by mistake. So let me put things like this. This is a field where, I mean, 6 months ago, 8 months ago, more or less, large language models did not exist. So, I mean, I am more on Jan LeCun's side, who says that basically this hype about large language model will last 3-4 years. And then these things will just disappear and substituted by something different. So what are we talking about? About the fact that artificial intelligence will become more and more capable to reproduce complex tasks. Definitely, I think that energy-based models are much better than what is available now. It will be better in the future. But so for sure there will be applications in the education, as rightly Alberto and Francisco pointed before, but also in other things. For instance, we are beginning to experiment on a very stupid thing. I mean, these things are very effective in writing code. And we know that one of the problems we encounter is the fact that usually in astronomy, codes are written by astronomers who don't have a software engineering degree. They are poorly documented, they are poorly written, they are not easy to export in different environments. And together with some friends here at the engineering department, we are starting to use this model to build chunks of software which are much more robust, much more reliable, and which can be preserved for a long, long time. So, for instance, I'm quite sure that this will make an impact on everyday life. And most of the routinary part of the software will be written with these models in a few years. There is no longer need, to write. Of course, new algorithms, new development, at least for the moment being, we have to write them by ourselves. But there are a lot of possible applications in annotation of data. For instance, annotation of astronomical image, in better usage of available data, for instance, in pointing the user to the right resource. I mean, I foresee a lot of application for this. It will not be revolutionary in our field, but for sure it will be of great help.
Yeah, I think I agree that, you know, I think there's, with the right development, this could potentially solve our education problem, as certainly as Alberto was pointing out. But one question we've had on the YouTube channel is, you know, is there a common? It's great that we train all these grad students, or you know, whether they're doing masters or PhDs in these very good data science fields, and then they decide that they don't want to continue in academia and they want to they go into the big private companies, and we have this huge hemorrhage or brain drain or whatever. Do we have any strategies for that?
I want to be first.
Pepe, please.
2 days ago, I lost one of my former PhD students who did a wonderful work on using CNN trained on ImageNet, you know, for galaxy classification, who went to a data security company for a salary which was 4 times higher. There is no way we can do anything. I mean, until astronomical salaries are
Or
what they are
astronomical.
now, are not become not astronomical. I mean, just to make a comparison, we could pay him 200,000 euros per month. This company in Dubai offered him 8,500 euros per month. So of course, if you are not strongly motivated by passion for astronomy, you go to a private company.
And just to add to what Pepe was mentioning, so the salary is probably one, if not the biggest problem, but it's not the biggest. I don't know if it's the only problem. It's because in astronomy we are position starved as well, right? So especially how do we want to intend astronomers who are well educated in computer sciences and software engineering and in more fundamental mathematical concepts to stay in astronomy if they will need to probably to work as postdocs in very unstable positions for 5 to 10, sometimes 15 years before they land in a more or less stable position, right? So it's almost impossible. Like it's a no-brainer for a student or for a previous student who passes his PhD or her PhD or their PhD to stay waiting for perhaps a position after 10 or 15 years, right? While the company, like a quarter, like a few blocks away from their house, is offering them like a salary that sometimes is 2 or 3 or 4 times higher than the salaries that they are going to have after 15 years. Like, makes no sense, right? So,
yeah. Francisco, thoughts?
No, I mean, if you think of the amount of positions and the amount of available and the amount of people that are being formed, are trained, there will have to be some spillover, let's say.
Yeah.
What is the right amount? I don't know. It's very difficult, but I think.
Yeah, and I think one comment I'll make is that it is potentially the success of astroinformatics, particularly within the broader field of astronomy, that we actually produce the most employable students, whatever, outside of our field.
Yeah, I've seen many students that have told me this.
Yeah, and it's, you know, there's a good incentive for people to put more money into this to support these types of activities because of that broader putback we can put in. So we're almost at time. So I will like to give you each a couple of minutes just for your final thoughts on the things that we've been discussing, or anything you feel that we did not discuss. So let's start with Pepe.
I think I think we discussed about quite a lot of topics actually. No, I think not much is missing. So it's fine for me.
Francisco?
Well, just not to repeat what we have discussed, just say that what I see is a huge change in the last 10 years. So I'd like to end with a positive the side of things. So I really think that this area has changed a lot. And as Pepe mentioned, interdisciplinarity is not an obscure thing. It's encouraged by the funding institutions. Astroinformatics has grown a lot, and I think we play a very important role in astronomy to help the community adapt to the future and help astronomers, students to have more options. So I think, yeah, we're having an important role at the moment, I think.
I am buying this to adapt to the future. It's right. It's true. It's right to the point.
Yep.
We help the astronomical community to adapt to the future because that's real.
Yeah, because if we can't figure it out, they're never going to.
Yeah.
Yeah, and one of the reasons why like Astroinformatics has been doing this is also because it has been helping astronomy, so the language that we use in astronomy to approach a little bit the language that is used in computer science related fields, right? And in the same way that we have been doing this with language between fields, we also have been doing this with language between countries as well, right? Because like
Yes.
astroinformatics is between, like when we see to the different astronomy subfields, astroinformatics is probably one of the fields where we have like more representativeness between poorer and richer countries, together with educational astronomy as well, right?
That's true.
And this is also because data has becoming freer and freer and freer. And computational resources, although they are a problem for poorer countries, we always try to find some way to beat them. I use it to buy lots of machines in eBay and secondhand machines to be able to do like large data processing when I had to do it, right? But anyway, so like Astroinformatics is it's helping to create this bridge, this common language between fields, and it can help furthermore to create a bridge between the languages and culture, like working cultures between different countries as well. Like I think it's my thing that I think that Astroinformatics is ideally poised to help this happen in the next few years. So.
Good. Yes. So I think, some of these recommendations will appear in the white paper, and our overall recommendation is we need more money. We need more resources, because then we can develop even better these things to help sustain.
Yeah, and actually, one of the things that I feel that is also important, just to add to what you said, Matthew, beyond more money, and I think one of the important things is money that can cross borders.
Yes.
Like, because it's sometimes very easy to get money that is self-contained in certain countries to a single university, but even collaborations between different universities it's hard, right? So, and imagine between different countries, like you get money in the US, it's hard to make that money flow to Europe or to Africa or to South America or to Asia, right? Or vice versa, right? So this should be easier to do, right?
Well, I don't think money ever flows into the US, so.
Sometimes it does.
Yeah, I know, but the perception is, but I think it's an important thing. Yes,
Yeah,
and it's, for an organization like S20 or G20, that's where those sort of barriers can be reduced so that we can get this, as you identify, this far more international development going on. Okay, well, I'd like to thank all of our panel speakers for your time. I think this has been an interesting panel, and I'll hand it back to Ashish and Pranav.
Thank you, Matt. Thank you, Ashish.
Thank you, Matthew, and
Very
all the
much fun.
panelists. This is excellent. And like all the panels before, we hope to see the feedback from this go back into the white paper, and then we'll be compiling that. So this brings us to the end of the Science 20 policy webinar, Astroinformatics for Sustainable Development, under the aegis of the G20 presidency of India. So we had many exciting talks and corresponding panels where several critical points worth following up were discussed. As the data volumes are growing, enable more people to use existing data, enabling better collaborations, enabling the rich human capital, especially from the historically excluded classes, to participate in the process of science, looking forward to increasing amounts of data from space as humanity fledges its wings, using ML and AI more effectively while keeping it bias-free, and so on. The content from this meeting will also feed into a project that is being planned, the documentation of computation-driven astronomy. It'll form a good resource for creating effective policies, for instance, the experiences that various panelists and all the speakers mentioned. The videos will continue to be available on INSA's YouTube channel. You can reach us with further feedback there, and you also know where to find us. A big thank you to all the speakers and panelists, especially the moderators, and I look forward to the resulting white papers. Also, thank you to INSA for hosting, including to Zubinder, who ensured that the meeting platform worked flawlessly. I will now hand over to my co-convener of this meeting, Pranav Sharma, for closing remarks on behalf of INSA. Pranav.
Thank you, Ashish. Last 3 days have not only been enriching, but also very exciting in terms of understanding how modern research and technology would shape the policy world, and also effectively the face of what we now call multilateralism. Having said that, we have very effectively, and not only very effectively, but I think most importantly realized that in the public space, how science diplomacy works, especially when it comes to collaborations across geographical regions. I was in a meeting day before yesterday of the science advisors here in New Delhi, and something very interesting came up, wherein ideally there are 3 scenarios for science diplomacy that we usually talk about, especially when it comes to global collaborations, regional, sub-regional, and others, wherein we talk about science for diplomacy, science in diplomacy, and diplomacy in science. But another very interesting aspect that came up, wherein we utilize international relations and diplomatic tools for ensuring the measures that are taken within the scientific realm are of great standard. In that direction, a lot of work was taken up by the G20 and also the Science 20, and a lot of academies convened together. We talked about various aspects of not only science policy formulations, but also how advisories work, how disruptive technologies would shape the world. And one of those meetings where Ashish was also present, we came up with the idea that, it would be of great interest for global governance that an international expert panel or an international expert group of sorts could emerge through consultation, wherein scientists who are looking at fields that are emerging, which would become prominent, say like 10 years, 20 years down the line, consult the governments and tell them how and where to invest, what are the things that we need to look at. Astroinformatics being one of that disruptive science, which has great proven track record, is the ideal case scenario. And that is why we had this meeting, for looking much deeper into how astroinformatics as the 21st century disruptive science can, and what can it do for sustainable development, and how can we look into the policy formulations. The work that would follow this webinar would be to formulate, concise the white papers that all of us have been working together. We will come up with recommendations that will be sent to the Secretariat and other places. And effectively, we have started this initiative with India. We will take it up again in Brazil. We'll follow it up in South Africa, so that we see things through. And because all 3 countries in the G20 Troika are very important for astronomy research, be it the location of observatories or the geopolitical location of the global south. A lot of us will be deeply invested in these networks. Having said that, we would also be sending recommendations to the intergovernmental science diplomacy networks, As some of you know, that the European Science Diplomacy Conference is coming up later this year, and other similar avenues would open wherein we would push the ideas that have been discussed here, which have emerged from the Science 20 policy discussions on astroinformatics for sustainable development. Thank you so much to all the panelists who were here yesterday and today. It was great science, great ideas that were discussed, and we really look forward to working together and working more effectively in the near future. Thank you so much. Have a great morning, afternoon, evening, night from wherever you.
Thank you, and
Thank
take care,
you.
Ashish. Bye.
Thank you. Bye.
Bye.